How does a cold, dark molecular cloud give birth to a shining star? What hidden processes unfold inside a protostar before nuclear fusion begins? Why must young stars shed gas and dust before they can fully emerge into the light? In the vast darkness between the stars, enormous clouds of cold gas and dust drift quietly through space. These are the stellar nurseries of the universe, known as molecular clouds. Immense collections of mostly hydrogen gas, laced with helium, and trace amounts of heavier elements. They range from thousands to millions of times the mass of our Sun, and can stretch across hundreds of light years. And they are extremely cold, allowing gas to clump together into high-density pockets. Within these cosmic clouds, the temperature is only a few tens of degrees above absolute zero. At such low temperatures, atoms move sluggishly, and the gas gathers into ever denser pockets. To an outside observer, such a cloud appears almost completely dark. The dust grains mixed in with the gas are so effective at blocking light that they hide whatever lies inside. Starlight from beyond is extinguished by these thick veils of dust. Only an opaque shadow remains against the starry background of space. Deep within this obscuring haze, the environment is serenely cold and still. The cloud's interior is shielded from harsh ultraviolet radiation by its own dust, creating a haven of darkness. In this quiet refuge, molecules can form, most abundantly hydrogen, but also more complex species, and tiny dust particles accumulate icy coatings. The entire cloud drifts slowly in a galactic spiral arm, so diffuse that a cubic centimeter of its interior may contain only a few hundred atoms on average. Yet the cloud is massive and sprawling, laden with raw material that could one day ignite into starlight. Astronomers estimate that our Milky Way galaxy contains thousands of such molecular clouds. Together, these massive clouds hold a significant fraction of all the gas in the galaxy. These hidden assemblages of matter are truly cosmic cradles where new stars will be born. From afar, however, they betray no hint of the brilliant lights they will eventually unleash. Occasionally, a molecular cloud is revealed at its edges by the glow of nearby stars or the soft luminescence of excited gas. We see these nurseries as dark silhouettes only when set against a luminous backdrop, such as a bright nebula or the star-dusted Milky Way plain. One famous example is the Horsehead Nebula, a dark plume of obscuring dust seen in front of a glowing hydrogen cloud. More often, these stellar nurseries remain invisible to ordinary telescopes, inscrutable black patches in the sky concealing their treasures. Even so, sensitive instruments detect their presence. Radio and infrared observations can trace the faint signals of molecules deep inside the clouds, mapping their vast, cold interiors. Inside these clouds, all is darkness to the eye, but not absolute silence. Within the chilly gloom, gravity is ever at work. The gas and dust, though tenuous, feel the pull of their own collective gravity. Over millions of years, subtle disturbances ripple through the cloud, perhaps a passing shockwave in the galaxy's spiral arm, or the distant blast of a supernova, sending a gentle compression through the gas. In other cases, random motions within the cloud cause some regions to grow a bit denser than their surroundings. In this way, nature sows the seeds of stars. Small pockets where, by chance, or by an external trigger, matter gathers just slightly more tightly, tipping the balance ever so subtly. For as long as the internal pressure of the cold gas can resist gravity, the cloud remains in a delicate equipoise. But the balance is precarious. In the coldest, densest corners of the cloud, pressure is low, and gravity's grip begins to tighten. When a region of the cloud grows massive and concentrated enough, gravity inexorably starts to dominate. The quiet darkness of the cloud is about to be broken. In these hidden pockets, still invisible and inscrutable from outside, a slow and subtle collapse has begun. Gas that once drifted aimlessly now flows inward, drawn by an unseen force toward a common center. A hush still reigns across the cloud at large, but in the depths of one dark core, the long journey towards starlight is underway. At the center of the collapsing core, gas rushes inward and gathers into a growing ball. The infalling material heats up as it descends, converting gravitational energy into thermal motion. At first, the collapsing gas can shed much of this heat as radiation, which allows the collapse to proceed unhindered. But as the density increases, the core becomes less and less able to radiate away its energy. It starts to trap its own heat, and the temperature inside climbs. Fortunately, the dust within the infalling gas provides a means to shed this energy. As the gas heats, tiny grains absorb the thermal radiation and themselves warm to perhaps only 60 to 100 kelvins, still extremely cold by human standards. They then radiate that energy at far infrared wavelengths, a part of the spectrum where the surrounding cloud is relatively transparent. In this way, the dust acts as a cooling valve, allowing the core to continue contracting further and further. Even with this assistance, the collapse cannot continue unchecked forever. As more and more gas piles into the center, the innermost region becomes extremely dense and hot. Eventually, a small core forms where the rising gas pressure manages to slow the infall. For a brief period, the collapse stalls in this inner zone, and shock waves ripple through the nascent core as incoming material crashes into it, heating it even more. But this respite is only temporary. When the core's temperature reaches roughly 2000 degrees, a dramatic change occurs. The hydrogen molecules that dominate the gas begin to break apart into individual atoms. This molecular dissociation gobbles up thermal energy, causing the gas pressure to plummet. Without enough pressure to counteract gravity, the collapse resumes with renewed vigor. The core, now composed mainly of atomic hydrogen, contracts even further, and the central temperature jumps higher once again. In the final stages of this rapid infall, the density of the central object soars, and the gas becomes opaque to its own radiation. Trapped heat builds until, at last, the growing internal pressure pushes back. The collapse slows and finally comes into balance. The infant object has reached a new equilibrium. The inward pull of gravity is now matched by the outward push of hot, pressurized gas. Astronomers call this state hydrostatic equilibrium, a delicate balance of forces that will characterize the star throughout much of its life. When this first balance is achieved, the newborn star can truly be called a protostar. It is not yet powered by nuclear fusion. For now, the heat from its own gravitational contraction is what supports it against collapse. The protostar remains deeply embedded in its parent cloud, an embryonic star still cocooned in the gas and dust from which it formed. The protostar continues to gain mass as surrounding material rains down upon it. Because the collapsing gas carries some rotation, it does not fall straight in, but instead forms a swirling accretion disk around the new star. Through this disk, matter spirals inward, feeding the protostar even further. But the spinning system also finds an outlet for some of its excess energy and angular momentum. Twin jets of gas erupt from the protostar's poles. These bipolar outflows, observed as luminous Herbig-Haro jets when they slam into the surrounding nebula, carry away angular momentum and heat, allowing the young star to continue accreting mass. In the midst of this cosmic construction, The protostar's core continues to grow ever hotter and denser. At a few million degrees, it even begins to fuse a rare form of hydrogen called deuterium. This fusion releases additional energy and creates an outward pressure that further slows the collapse, but it does not stop it entirely. The protostar still has some distance to go before it reaches true stability. All of this turmoil remains hidden inside the stellar nursery. From the outside, we still see nothing of the infant star in visible light. The protostar's brilliance is veiled by the thick envelope of gas and dust around it. Only longer wavelength radiation, infrared light and radio waves, can escape from this dusty cocoon to the wider universe. When astronomers point sensitive infrared telescopes at these dark nebulae, they detect the telltale warmth of embedded protostars. What appeared black to the eye glows faintly in infrared, revealing the presence of an otherwise invisible star. In images of star-forming regions, one can often see dark globules or pillar-like clouds with tiny bright embers buried within, signs of protostars heating up their surrounding dust. In fact, small isolated dark clouds known as Bok globules often contain one or two infant stars, completely hidden in visible light, but revealed by their faint infrared glow. In the deep interior of the collapsing cloud, a profound transformation is underway, but it remains shrouded from view under a cloak of dust and night. Gradually, the protostar grows in both mass and luminosity. Bit by bit, it depletes the immediate reservoir of gas in its vicinity. Strong stellar winds begin to blow from its hot surface, and the intense light it produces starts to push away the remaining infalling material. The accretion of new mass slows down. The thick envelope of gas and dust that once enshrouded the protostar begins to disperse, thinned out by the star's radiation and winds. What was once an opaque, lightless cradle is becoming translucent. Deep inside the protostar, a critical threshold is about to be crossed. After perhaps a few 100,000 years of sustained contraction, or a few million years in the case of a star like our Sun, the temperature at the very center of the young star climbs to around 10 million degrees. At that moment, a fundamentally new source of power is poised to awaken in the core. The long wait through the dark, hidden infancy is nearly over. The protostar stands on the brink of its transformation into a true star, ready for the spark that will ignite its nuclear furnace. And then, at last, the spark arrives. Deep in the protostar's core, the nuclei of hydrogen atoms are finally pressed and heated to the point of fusion. In that silent moment, the young star's heart catches fire with thermonuclear burning. Enormous energy is unleashed and floods outward from the core, generating an internal pressure that pushes back against gravity's inward pull. The remaining traces of collapse come to an end as a new equilibrium takes hold. The long night inside the star has given way to a true dawn. For the first time, the new star is producing its own light and heat from a self-sustaining source. It no longer needs to rely on the finite energy of contraction. Now it shines steadily from the fusion of hydrogen into helium in its core. A true star is born. Astronomers refer to this stable phase as the star's main sequence, the long adulthood during which it will spend the bulk of its life. With nuclear fusion continuously replenishing the star's internal heat and pressure, gravity is held in perfect balance. The young star, having emerged from its turbulent birth, now settles into a calm radiance that can last for millions or even billions of years. Freed from its natal cocoon, the The star's brilliance pours into space, and its invigorated stellar winds sweep away the last wisps of the birth cloud. Now multiply this drama by thousands. Stars are being born all across our galaxy in countless cosmic cradles hidden within vast nebulae. Most stars do not form alone, but in clusters or groups, siblings emerging together from the same cloud. Our own sun is thought to have been born in such a cluster, long since dispersed. At any given moment, somewhere in the Milky Way, a dark cloud is quietly collapsing and giving rise to new stars. Starbirth is an ongoing process spread throughout the galactic disk. The Milky Way contains thousands of molecular clouds massive enough to spawn stellar clusters. Together, they form a vast network of stellar nurseries strewn along the spiral arms. For example, consider the Orion Nebula, a stellar nursery about 1,300 light-years away. To the naked eye, it appears as a faint patch of light in Orion's sword. But through a telescope, it blossoms into a glowing cavern of gas and dust, lit by a cluster of massive young stars. The Orion Nebula alone contains hundreds of recently formed stars, all carving their way out of the remaining cloud. It is a magnificent showcase of ongoing star formation in our cosmic neighborhood. Those massive infant stars in Orion pour out intense ultraviolet light and powerful stellar winds. Together, they carve out the nebula's interior and cause the surrounding gas to glow in rich hues. Along the fringes of the illuminated nebula, dense pillars and globules of dust still hide smaller, fainter protostars. In time, the radiation from the central stars will erode these dusty cocoons, allowing the baby stars within to emerge and join the cluster's brilliance. In the Eagle Nebula, about 7,000 light-years away, iconic structures known as the Pillars of Creation rise from a cloud of gas and dust. These towering columns, famously photographed by the Hubble Space Telescope, owe their shape to nearby hot young stars whose radiation is sculpting the cloud. New stars are forming within these dusty towers. Tiny, dense kernels of gas inside the pillars, called evaporating gaseous globules, or EGGs, shield pockets of material from the surrounding onslaught of ultraviolet light. Within each EGG, a protostar may be taking shape, hidden inside its protective cocoon. But as time goes on, the radiation will erode these globules. The newborn stars inside will be unveiled, often appearing as bright points at the pillars' tips. Modern telescopes have begun peeling back the mystery of these star cradles. The James Webb Space Telescope's infrared eyes, for instance, have pierced the dust of the pillars of creation to reveal a multitude of newborn stars that were previously invisible to us. By identifying far more young stars and measuring the gas and dust in such regions, Webb's observations are helping astronomers refine their models of how stars emerge from their natal clouds. With each new generation of instruments, we gain a clearer view of star birth in all its stages. Across the Milky Way, similar cradles of star formation abound. In the Carina Nebula, for example, immense walls of gas, sometimes nicknamed the cosmic cliffs, mark where a stellar nursery is being excavated by brilliant young stars. Elsewhere in the galaxy's spiral arms, giant molecular clouds harbour clusters of embryonic stars that remain shrouded in dust, detectable only in infrared or radio wavelengths. Each region has its own character and scale, but all are sites where darkness is giving way to starlight. Even a small, relatively quiet, dark cloud can give birth to stars. For instance, the Rho Ophiuchi cloud complex, only about 450 light-years away, is currently forming dozens of low-mass stars. These faint newborn suns remain almost completely invisible in optical light, yet they glow softly in the infrared. Some stellar nurseries preferentially produce such lower mass stars, while others, often the more turbulent clouds, spawn hefty, short-lived stars that will one day explode as supernovae. The variety is enormous, but the underlying process is the same. We observe these cosmic cradles using every tool at our disposal. Optical telescopes capture the beautiful glow of ionized gas around young star clusters. For example, the rosy hydrogen light in nebulae like Orion or Carina. Infrared observatories peer through dust to reveal the warm embers of protostars still embedded in their clouds. Radio and millimeter wave telescopes detect cold molecular gas and dust, mapping out the raw material fueling star formation. By combining views from across the spectrum, astronomers piece together the story of star birth from the initial cloud collapse to the moment a new star shines free. High-resolution imaging has even caught dramatic details. In regions that once looked amorphous, we now resolve shockwaves and jet-like streaks of gas blasting out from newborn stars. Each such discovery, be it a protostellar jet, a dusty disk, or a hidden cluster of infant stars, adds another piece to the puzzle. Bit by bit, astronomers are unraveling how these stellar nurseries operate. They are gradually learning how infant stars grow within them. Those effects are profound. Massive young stars, though few in number, dramatically transform their surroundings. Their searing ultraviolet radiation ionizes vast swathes of the parent cloud, causing it to glow, while powerful stellar winds sweep out great cavities in the gas. This combination of winds and radiation can compress some neighboring regions even as it disperses others. And the cycle of star formation often propagates itself. A nearby supernova explosion can send a shockwave crashing into a molecular cloud, triggering a new round of star birth. In this way, the formation of one generation of stars can induce the formation of the next, like cosmic dominoes falling through the ages. From glowing nebulae in our own galaxy to distant galaxies ablaze with starbursts, the formation of stars lights up the cosmos in a continual cycle of creation. Each bright young star that emerges from its cloud adds its brilliance to the grand tapestry of the universe. The darkness of a molecular cloud gives way to starlight, and clusters of newborn suns drift away to take their places in the galaxy. In these cosmic cradles, we witness the universe in the act of creation, the quiet emergence of brilliance from darkness, repeated in countless forms across time and space. Here, at last, a star is born, and its journey has only begun. In the silent darkness of a star-forming nebula, a new life is taking shape. Deep within a cold cloud of gas and dust, gravity draws matter inward to a single gathering point. As more gas falls in, the infant protostar grows heavier and hotter at its core. Nearby, other nascent stars are also coming to life. But this particular one is different. It is accumulating far more mass than its siblings. Unseen and quiet, the cosmic cradle nurses a giant in the making, one destined to shine with exceptional brilliance. From the moment a star is born, its fate is sealed by one fundamental trait: its mass. This single property acts like the star's cosmic inheritance, determining everything that follows. A small star, with only a fraction of our sun's mass, will live quietly and humbly, glowing gently for many billions of years. But a star born with dozens of times the sun's mass enters life with a grand destiny. To grasp that scale, a star 50 times the sun's heft packs in material equivalent to millions of Earths. With such immense weight, its core ignites with ferocious intensity, setting the stage for a short yet spectacular existence. Mass is the secret script of a star's life story. A greater mass means stronger gravity, squeezing the star's core, leading to higher temperatures and pressures. In a colossal young star, the core becomes a furnace, tens of millions of degrees hot, where hydrogen atoms fuse into helium at a prodigious rate. Energy pours outward from the core, and the newborn giant star begins to shine with a fierce light. Even as a mere infant on the cosmic timescale, it already blazes far brighter than stars, much older and smaller. There is a minimum weight needed for a newborn star to truly ignite. If a forming star is too small, it cannot squeeze its core hard enough to spark the fusion fire. Such underweight clumps linger as failed stars, dim, glowing embers known as brown dwarfs. These failed stars glow only with leftover heat and gradually cool over time, never igniting the stellar fire. It is a reminder that only above a critical mass can a true star be born. But for the protostar that gathers ample mass, a dramatic transformation occurs. The fuse is lit, and it becomes a living star. And when a star is born with far more than the minimum mass, it doesn't just flicker to life, it erupts into brilliance, announcing itself as one of the cosmic giants. These massive stars are not only defined by their weight, they rapidly distinguish themselves by sheer power. A star, only a bit heavier than our Sun, may burn several times brighter, and 110 times the Sun's mass can outshine thousands of ordinary suns. As mass grows, the star's luminosity soars dramatically. It is as if each extra lump of matter feeds an exponentially larger flame. In this way, mass bestows a kind of cosmic royalty, an elite status among stars marked by extraordinary brilliance from the very start. Such titanic stars are precious rarities in the cosmos. In any stellar nursery, nature forms far more small, faint stars than brilliant behemoths. For every star destined to become a giant, hundreds of smaller ones quietly take shape in the background. It is as if the nebula spares most of its material for common stars and reserves only a select portion for the truly massive. This select few will dominate their cosmic neighborhood, shining with fierce light that dwarfs the combined glow of their lesser kin. Consider two newborn stars forming in the same nursery, one destined to be a behemoth, the other a run-of-the-mill smaller star. At first, both ignite and join the cluster's glow. The massive one blazes intensely, outshining its petite sibling by orders of magnitude. But fast forward a few million years, the giant will have already burned out or exploded, while the small star will still be shining gently, scarcely aged at all. The dazzling elder lived gloriously but briefly. The unassuming younger star persists for epochs. Such is the contrast written by mass, a cosmic tale of the tortoise and the hare. From birth onward, mass whispers the promises and the limits of a star's life. It dictates not only how brightly the star will shine and how long it can burn, but also how it will perish. A modest star might end its days as a faint ember, quietly fading into a white dwarf. A truly massive star is destined for a far more dramatic farewell, a cataclysmic explosion that will scatter its enriched guts across space. All of these possibilities lie coded in that initial measure of mass, decided in the star's natal cloud. Now the giant star has truly awakened, radiating with almost unimaginable power. What was once cold, dark gas has become a beacon of intense light and heat. Bathed in the star's glow, the surrounding nebula shines in response. With its massive fuel reserves ignited, This newborn giant pours energy into space on a scale that defies ordinary experience. Such is the legacy of great mass, the birth of one of the brightest flames in the universe. The energy pouring out of a massive star is almost beyond comprehension. Once the giant has ignited its core, it radiates a brilliance that can light up the cosmic night. Such a star shines tens of thousands, even millions, of times more brightly than a star like our sun. Across great distances in space, it stands out like a lone beacon, its light dominating everything around it. In fact, in clusters of newborn stars, the few massive members can produce more light than all their hundreds of smaller siblings combined. In the darkness of its birth nebula, this single brilliant sun can transform the scene, turning nearby clouds into glowing vistas under its intense illumination. From afar, it appears serene, but up close, a massive star would be an awe-inspiring yet terrifying sight. Its surface boils and seethes under the onslaught of energy from within. Giant convective cells and streams of plasma race outward, only to be forced back by the pull of gravity and the weight of the layers above. The star's outer atmosphere is whipped into a frenzy by magnetic fields and the intense light pressure. In every patch of its stellar surface, countless photons are born each second and rush away, as though the star is on fire from every inch of its being. This tumult is hidden beneath the star's brilliant glare, but it hints at the raw power sustaining that light. If a spacecraft were to venture near this star, long before it arrived, it would be immersed in unearthly brilliance. The surrounding space would be aglow with a bluish daylight, and any nearby objects would cast sharp, stark shadows. Closer in, the star's ferocity would dominate everything. Its radiation would flood the spacecraft's instruments, and its sheer light would be blinding. In the vacuum of space there is no sound, yet one can imagine the deafening roar such power might produce. It is a journey only robotic probes could dare. No living thing could withstand the intense energy roaring from the stellar surface. This giant star's light is not a gentle golden glow, but a fierce blue-white blaze. Its surface is tens of thousands of degrees hot, far hotter than the sun's, giving it that bluish-white hue of extreme heat. It pours out torrents of high-energy photons, including ultraviolet light that our eyes cannot see. That ultraviolet energy electrifies the surrounding gas, making the star's birthplace itself shine. What was once an invisible, cold cloud now becomes a luminous nebula under the star's powerful radiance. In the great nebula of Orion, a few newborn massive stars cause the entire cloud to glow, revealing a celestial vista of pink and purple gases. At the heart of this brilliance lies a furious engine of nuclear fusion. Deep in the core, pressures are so enormous that hydrogen is fusing into helium at an unbelievable pace. In each passing second, the star converts millions of tons of its own mass into pure energy. This energy fights its way from the core to the surface and then streams out into space as light and heat. The result is a continuous outpouring of power, a stellar inferno whose luminosity dwarfs that of smaller stars. Looking at such a star from afar, one is witnessing a colossal furnace blazing steadily in the cosmic dark. So powerful is this brilliance that its radiation pushes against the star's own gases, a pressure that will gradually drive some of the star's mass into space as stellar wind. A single massive star's brilliance can be visible across immense cosmic distances. Even from thousands of light years away, such a star can outshine closer, lesser stars in the night sky. Some of the bright stars we see twinkling overhead are in fact these distant giants, their light reaching us after journeying through space for ages. For example, Rigel, the blue supergiant marking Orion's shoulder, lies around 800 light-years away, yet is among the brightest stars in our night sky. Its brilliance is so great that it lights up clouds of dust in its vicinity, revealing a faint reflection nebula in that region. It is a humbling sight, a point of light that seems small to our eyes, yet in reality is an immense beacon blazing with the power of millions of suns. These stars serve as cosmic lighthouses, signaling their presence across the vast gulf of space. There is something almost intimidating about this kind of stellar brilliance. From many light years away, the massive star looks like a tranquil blue-white beacon. But if you could approach it, the experience would be overwhelming. An ocean of light and radiation flooding space. The star's beauty is matched by its ferocity, a reminder that in the cosmos, great beauty often goes hand in hand with immense power. But such furious brilliance has a price. To shine so intensely, the massive star must consume its nuclear fuel at a staggering pace. In the heart of the star, hydrogen is being converted to helium millions of times faster than in a smaller star. This extravagant energy use means the giant cannot sustain itself for as long. The brightest flames burn through their fuel quickly, foreshadowing a life that will blaze briefly before exhaustion sets in. Time flows differently for the giants of the cosmos. A massive star that blazes so brilliantly cannot afford to burn slowly. It lives on fast forward, rushing through stages of life that a smaller star would leisurely stroll through over billions of years. In mere millions of years, the giant exhausts the prime fuel of its youth. The same mass that granted it such power also demands that it be spent quickly, forcing the star to live intensely and die young. In cosmic terms, these giants are ephemeral. Imagine the galaxy as a garden. Most stars are like ancient trees that endure for ages, but massive stars are like brilliant flowers that bloom fiercely and wither away in short order. They expend their fuel in a great burst of vitality, shining with unmatched brilliance while they last. Then, before the rest of the universe has much chance to notice, they begin to falter. It's a cosmic irony. The most brilliant stars live the shortest lives. A star can either shine modestly for an exceedingly long time, or blaze with incredible intensity and spend its fuel quickly. The difference in lifespans between small and large stars is staggering. A star like our Sun enjoys a life of around 10 billion years, and a tiny red dwarf can burn for hundreds of billions, or even trillions of years, effectively outliving the current age of the universe many times over. In contrast, a blue-white giant might last only 5 or 10 million years. That is just a few moments on the cosmic clock. In fact, no red dwarf has ever died in the entire history of the universe so far, whereas the most massive stars are often born, live, and die within the span of a single geological era on Earth. We can see evidence of this accelerated life cycle in some of the stars visible in our own sky. Take Betelgeuse, the bright red star marking Orion's shoulder. Though it gleams prominently on winter nights, Betelgeuse is a relative youngster, perhaps only 8 or 10 million years old, a tiny fraction of the Sun's age. Yet Betelgeuse has already exhausted the hydrogen fuel at its core and swollen into a red supergiant, a sign of advanced age for a star. The Sun, by comparison, won't reach that stage for billions more years. This means Betelgeuse, despite being vastly younger than our Sun in absolute years, is much closer to the end of its life. A massive star races through its life stages with breathtaking speed. After burning through its hydrogen, it doesn't quietly settle. It immediately begins fusing helium left behind in its core. The star contracts and then expands again, turning into a supergiant. In its deep interior, new layers of fusion ignite one after another. Carbon, oxygen, neon, and so on, each fuel burning faster than the last. The giant star becomes like an onion in structure, shells of different elements stacked inside as it desperately tries to stave off the inevitable. Where a smaller star might linger in each stage for eons, the massive star spends mere millennia or less. In the final phase, when iron accumulates in its heart, an element that yields no energy from fusion, the star has reached a dead end. Its brilliant life, so vigorous and short, is poised on the brink of a violent transformation. It has burned its cosmic candle fiercely to the end, and now that flame is almost extinguished. In fact, because of their brief lifespans, some of the massive stars we observe in distant skies may no longer exist. Their light takes so long to reach us that by the time we see their brilliance, the star itself might have already perished. We are gazing at ghosts of long-gone giants shimmering across the light years. Yet, even among massive stars, no two stories are exactly the same. There is another factor, apart from sheer mass, that influences how a star's life unfolds and how it will meet its end. It is the star's original makeup, the mix of elements it contains from birth. Most of a star is hydrogen and helium, but the trace amounts of heavier elements, its metals, can subtly change how it burns and how it loses its mass. These differences in composition, known as metallicity, play a crucial role in shaping each giant star's destiny. Every star carries a kind of chemical fingerprint from the time and place it was born. In the case of massive stars, this fingerprint, the mix of elements heavier than helium in their makeup, can steer the course of their lives in subtle but important ways. Astronomers call this mix, metallicity, a star born in the early universe, when hardly any heavy elements existed, behaves differently from one born later, after eons of cosmic enrichment. In essence, the recipe of a star's ingredients can alter how it shines, how it ages, and how it dies. Over 13 billion years ago, before galaxies had fully formed, the universe was a dark place. In that primordial night, the very first stars, kindled out of collapsing clouds of almost pure hydrogen and helium. These pioneering giants had virtually no metals at all, no carbon, no oxygen, no iron, because those elements did not exist yet. Without heavy elements to cool the gas, the clouds that collapsed into stars had to be enormous. As a result, the first generation of stars is thought to have been extremely massive, far larger than most stars today. They blazed hot and brilliant, and lived brief, furious lives, seeding space with the first heavy elements when they died. In doing so, they made possible everything that came after, future generations of stars, planets, and eventually life itself. As the universe aged, each generation of massive stars forged new heavy elements and scattered them into space. This meant that later generations of stars were born with some fraction of carbon, oxygen, silicon, and other elements mixed into the primordial hydrogen and helium. Those trace ingredients act like a cosmic catalyst. A small pinch of metals can profoundly change the flavor of a star's life, much like a spice can transform the taste of a soup. In star-forming clouds, they allow gas to cool and fragment more readily, leading to many smaller star embryos instead of a few huge ones. In the stars themselves, the added metals increase the opacity of the gas, meaning starlight has a harder time escaping. As a result, radiation builds up and pushes against the star's outer layers more forcefully. In practical terms, higher metallicity gives a massive star a kind of stellar wind at its back, literally. The intense light of a metal-rich giant star pushes on all those metal atoms in its outer layers, driving a powerful stellar wind. Over its lifetime, such a star can shed a considerable amount of mass into space. Sometimes a massive star with enough metal content will even lose its entire outer hydrogen layer, exposing the hot core beneath. Without its hydrogen cloak, it transforms into a rarer, fiercely luminous object, one that tells us it has been heavily sculpted by wind and loss. Meanwhile, a massive star, born with few metals, lacks this strong wind and tends to hold on to its mass. It remains more compact and hot, often staying blue throughout its life. When it dies, it does so with nearly its full bulk intact, which can produce an extremely energetic explosion or even cause the star to collapse almost directly into a black hole. By contrast, the metal-rich star that slimmed down may leave a smaller remnant, like a neutron star, after a comparatively gentle supernova. In this way, metallicity can tip the balance on a star's final outcome. And crucially, metallicity doesn't just affect the star's private life cycle, it also influences how that star interacts with its surroundings. The winds and tempests that massive stars unleash, partly driven by their composition, will go on to sculpt the cosmic landscape around them. These outflows blow enormous bubbles in the interstellar gas, eroding and shaping nearby nebulae. In some cases, the winds compress distant clouds, which can even trigger the birth of new stars. Long before a giant star meets its end, it is already profoundly affecting its cosmic neighborhood through the force of its stellar winds. We ourselves owe our existence to this cycle of cosmic enrichment. Our Sun is relatively rich in metals, about 2% of its mass, a legacy of countless earlier stars that seeded the gas from which it formed. That metal-rich birth enabled the creation of Earth and the diverse elements that make up life. Had the Sun been born in an environment with far fewer heavy elements, there might have been no rocky planets or people here to wonder at the stars. In this way, the lives of massive stars, through the metals they create, are deeply intertwined with our own. Massive stars do not wait for their final blast to begin shaping the cosmos around them. Even during their lifetimes, they continuously release streams of charged particles and gas from their surfaces, creating what astronomers call stellar winds. Unlike the breeze we feel on Earth, this wind is a fast-flowing outpouring of stellar material, blowing outward in all directions at incredible speeds. In the case of a hot, massive star, the wind can reach thousands of kilometers per second, carrying away the star's outer gases into space. For comparison, our Sun's solar wind is a mere trickle, carrying off an almost undetectable amount of mass, a gentle breeze next to the gale of a massive star. But a hot giant's wind can be millions of times stronger. Over time, these winds can eject an astounding amount of mass, in some cases comparable to several Earths each year, fundamentally altering the star's surroundings. As this fierce wind streams outward, it rams into the surrounding interstellar gas. Picture a cosmic snowplow. The stellar wind pushes and sweeps up the denser gas in front of it. A bubble of hot, thin gas forms around the star, expanding over the years. The boundary where the wind meets the ambient gas glows from the shock of the collision. Within the bubble, temperatures soar and the gas is tenuous, but at the edges, the swept-up material can become dense and brilliant, often ionized by the star's ultraviolet light into a fluorescent nebula. Even though an enormous storm is raging, it unfolds in near-perfect silence. In the vacuum of space, No sound carries from the stellar gale. The bubble expands quietly, like a silent explosion, with only light and motion to mark the turmoil. One famous instance is the bubble nebula in Cassiopeia, a gigantic, translucent sphere of gas about 7 light-years across, blown by the wind of a single energetic star. The handiwork of stellar winds can be seen in many nebula. In some astronomical images, we behold structures like delicate filaments and hollowed-out cavities in glowing clouds. These are often the direct result of massive stars' winds. One iconic example is the so-called pillars of creation, towering columns of gas in the Eagle Nebula. These majestic pillars are being slowly sculpted and eroded by the intense winds and radiation from nearby newborn stars. The tips of the pillars glow as they are heated and stripped away. Gas streams off into space from these evaporating peaks. Over time, those once solid columns will disintegrate entirely under the assault, dispersing into wisps, the signature of the massive star's relentless winds. In this way, the presence of a single giant star can fundamentally reshape its birthplace, blowing apart the nursery from which it emerged. When many massive stars are born together, their combined winds wreak even greater changes. In a dense star cluster, multiple giants unleash winds that merge into a colossal outflow. Instead of a single bubble, they can create a superbubble, an enormous cavity punched into the galaxy's gas. Such a cavity can span dozens or even hundreds of light years. Within it, the interstellar medium is cleared out and superheated. Along the edges of the superbubble, new shocks and ionized shells form where the collective wind slams into cooler gas. Whole regions of space can be emptied and energized by this teamwork of stellar winds, a prelude to the dramatic supernova events that will later follow as these stars reach the end of their lives. These stellar winds do more than just destroy. In some cases, they also sow the seeds for new creation. As a wind-driven bubble expands and its shock front plows into distant clouds, it compresses gas in those regions. That compressed gas can become the birth material for new stars. In this way, the violent winds of massive stars can trigger a new wave of star formation at the bubble's periphery, a cosmic cycle where one generation's outflows help spark the next generation's births. These winds also carry with them the products of the star's own nuclear fusion. As massive stars evolve, they create heavier elements in their interiors. Some of those elements, like carbon and nitrogen, make their way to the star's surface in later stages. When the star's wind blows outward, it drags these newly forged atoms out into space. Even before the star explodes, it is enriching its surroundings with the raw material for future planets and life. In extreme cases, massive stars can experience colossal eruptions, pseudo-supernova events, blasting off significant portions of their mass in a short time. In 1843, for instance, a star in the constellation Carina suddenly brightened to become one of the brightest in the sky. This star, known as Eta Carinae, was undergoing a great eruption, expelling an enormous shell of gas and dust around itself. What emerged from that event is a double-lobed nebula, a billowing shroud of debris that the star cast off. It was a dramatic example of stellar winds and outbursts in action, a giant star shedding its outer layers in a tempestuous convulsion. Such episodes are relatively rare, but they show just how powerful and unpredictable massive stars can be before their final end. Through their winds and outbursts, massive stars leave a lasting imprint on the cosmos around them. And importantly, such giants are seldom solitary. Most massive stars form alongside others, born in rich clusters where dozens or even hundreds of stars emerge together. In these crowded nurseries, the giants live among peers, sometimes interacting, sometimes competing for resources, always influencing their environment in concert. To truly understand these cosmic titans, we must see them as part of their stellar families, not just as lone beacons. Our journey now turns to those families of giants born together and the unique stories that star clusters tell. Stars are born not in isolation, but in communities. The same giant clouds of gas and dust that give rise to one massive star usually produce many others at the same time. In those stellar nurseries, dozens or hundreds of sibling stars take shape together. They range from the smallest red dwarfs to the rare massive giants, all sharing a common birthplace. These groups of stars, bound by their shared origin and often by gravity for a time, are known as star clusters. Imagine peering into a freshly revealed star cluster. The scene is a glittering swarm of stars crowded into a small region of space. Not long ago, these stars were cocooned in the same natal cloud, their light hidden by veils of dust. But the intense radiation and winds from the biggest stars have since blown much of that nebula away, unveiling a cluster of newborn suns. They shine together like a jeweled patch of sky, bright blue-white beacons intermingled with fainter golden stars. This is a cosmic family portrait. Stars of different sizes and colours, all born in the same celestial cradle. One can almost imagine these sibling suns sharing a youthful camaraderie beneath their natal nebula's glow, shining together in their cosmic nursery. If one could stand on a planet deep inside such a cluster, the night sky would be breathtaking. Dozens of nearby stars would shine brilliantly, far brighter than any star in Earth's sky, apart from our sun. Their combined glow might bathe the night in a perpetual twilight. In the cluster's core, darkness never falls completely. The collective starlight of the family is always present, a glittering backdrop to any skyward gaze. Some star clusters are near enough for us to see with the naked eye. The Pleiades, often called the Seven Sisters, is one such cluster, easily visible on a clear night as a tiny misty dipper of stars. In a telescope, the mist resolves into dozens of blue-white stars sprinkled together. They are all siblings, born from the same cloud around 100 million years ago, and they still drift through space as a loose family. The faint, gauzy glow around the brightest Pleiades stars is a reflection of lingering dust, perhaps a remnant of their birth cloud, which these stars light up like silver-blue fog. Looking at the Pleiades is like looking at a family of stars in its youth, still relatively close-knit after leaving their celestial nursery. What makes star clusters particularly special is that all their stars are nearly the same age. They started life together, like twins and triplets on a cosmic scale, except in this case, there might be hundreds of siblings. This means the only major difference between cluster stars is their mass. As a result, the cluster becomes a natural laboratory for stellar life cycles. In a young cluster, only a few million years old, you might already find the most massive stars swelling into red supergiants, or even ending their lives, while the smaller stars continue contentedly on the main sequence. Side by side, these stellar siblings make clear how strongly mass dictates fate. The hefty stars rush through their life stories, whereas the lightweights linger far longer. Observing a cluster is like witnessing multiple chapters of stellar evolution at once, each star at a stage set by its mass, yet all sharing the cluster's common birth time. It is akin to a slow-motion fireworks display in space. The massive stars burst forth brilliantly and vanish early, while the smaller ones glow steadily in the background. Star clusters come in all ages. Some survive for billions of years as tightly bound globular clusters. In those ancient families, the massive stars of their youth are long gone. Only their slow-burning smaller siblings remain, still orbiting together after eons. The brightest lights of those clusters are red giants and the combined glow of myriad dim stars, for the once blazing blue giants have faded into history. Yet the cluster endures, a cosmic retirement home of stars that outlived their giant brethren. Star clusters themselves do not last forever. Over many millions of years, the family gradually comes apart, after the cluster's massive stars have lived out their brief lives and exploded or faded. The gravitational glue holding the group can loosen, with no more gas cloud binding them and fewer heavy stars to keep them clustered. The remaining stars begin to drift away. One by one, they meander into the wider galaxy, carrying with them the shared memory of their origin. Our own sun likely experienced this long ago. Born in a cluster that has since dissolved, its stellar siblings now scattered unseen among the Milky Way's billions of stars. Yet before that dispersal is complete, something profound will happen to the cluster's giants. They will one day reach the end of their fuel and unleash the ultimate stellar fury. One by one, these massive stars will erupt as supernovae, titanic explosions that will briefly outshine all the other stars in their cluster combined. In those final blazing moments, the lives of the giant stars come full circle. Their violent demise will scatter into space all the heavy elements they forged, seeding new clouds and new stars yet to be. It is in destruction that they sow the seeds of creation, ensuring the cosmic cycle continues. The story of the giant stars will soon culminate in these explosive farewells, the spectacular deaths that both end a star's life and give birth to new possibilities. At the core of our newborn massive star, an extraordinary transformation is underway. Crushed by the star's immense gravity, hydrogen atoms are forced into unimaginably close quarters. Under these extreme conditions of heat and pressure, something miraculous happens. Hydrogen nuclei begin to fuse together, merging into new helium atoms. This process, nuclear fusion, releases a staggering amount of energy, the same energy that will make the star shine brilliantly in the cosmos. Deep inside this stellar furnace, 4 hydrogen nuclei ultimately join to form one helium nucleus. In the process, a small fraction of their mass is lost and transformed into pure energy, a conversion foretold by Einstein's famous equation. The core is flooded with high-energy radiation from these reactions, energy that slowly trickles outward through the star's layers. Some of it will eventually emerge from the star's surface as the warm glow of starlight that we see from across the galaxy. In a star as massive as this, the fusion of hydrogen proceeds through a particularly rapid chain of reactions. Rather than relying solely on the slower proton-proton fusion process that powers smaller stars, our massive star primarily uses the carbon-nitrogen-oxygen cycle as a catalyst for fusion. In this CNO cycle, trace amounts of carbon, nitrogen, and oxygen in the core help speed up the conversion of hydrogen into helium. This catalytic cycle allows the star to burn its hydrogen fuel even more ferociously, pumping out energy at a prodigious rate. At the center of the star, the crush of overlying mass produces pressures of billions of atmospheres. At such overwhelming pressure, atoms cannot survive intact. Their electrons are stripped away, creating a seething sea of bare atomic nuclei and free electrons. The material is packed many times denser than solid iron. In this strange realm, the gas behaves almost like a liquid or a metal, freely conducting heat and allowing the core to churn like a gigantic, molten heart. To truly grasp these extreme conditions, one can imagine journeying from the star's surface down into its depths. At the visible surface, the gas is fiery but tenuous, glowing at tens of thousands of degrees. As we descend, the light grows harsher and the heat intensifies. Deeper still, the gas becomes denser and the orange glow turns bluish-white under the soaring temperatures. Layer by layer, the pressure mounts. By the time we reach the core, the environment is utterly alien, a realm of blinding radiation and seething plasma where matter is compressed to extraordinary density. It is here, in this hidden furnace at the center, that the star's energy is born. The conditions at the center are almost beyond imagination. Temperatures climb to tens of millions of degrees, and matter exists as a seething plasma of charged particles. Atomic nuclei hurtle at incredible speeds, occasionally colliding head-on with enough force to fuse. Each fusion event not only produces a new helium nucleus and energy, but also releases ghostly neutrinos that stream outward unhindered, escaping the star entirely without a sound. In fact, the star's core is only just hot enough to make fusion possible. Protons naturally repel each other due to their positive charge, and even at tens of millions of degrees, direct collisions often lack the energy to overcome this barrier. Fortunately, quantum physics provides a subtle loophole, a phenomenon called quantum tunneling. It allows protons to occasionally slip through the electric repulsion barrier and fuse despite not having classically enough energy. Without this quantum quirk, the star's core might never ignite at all. The Sun and other stars owe their shine to this miraculous subatomic chance. One can scarcely fathom what it would be like to behold the star's core up close. It would be a realm of blinding brilliance and unfathomable heat, where the very air, if one could call it that, glows with constant nuclear fire. In this environment, the distinction between matter and energy blurs. Particles and light intermingle in a ceaseless, furious dance. It is an otherworldly cauldron, a place where the normal rules of nature are pushed to their extremes. This furious nuclear burning is precisely what holds the young star up against the crush of its own gravity. The core's energy output creates an outward pressure, a radiant force that balances the inward pull from the star's colossal mass. As long as hydrogen fusion continues steadily, the star remains in a stable equilibrium, neither collapsing nor exploding. From the outside, the star shines with a steady brilliance, pouring light and heat into space. A brilliance that, for a massive star, can be hundreds of thousands of times greater than that of our Sun. The sheer power output of the core is almost inconceivable. Every second, the star converts millions of tons of its mass into energy, an amount of matter equivalent to a sizable mountain being completely transformed into light, releasing an enormous flood of radiation. High-energy photons born in the core take a long random walk outward, bouncing countless times off particles in the dense interior before they finally escape from the surface as visible light. When they do emerge, the star's surface is searingly hot, tens of thousands of degrees, giving the young star a brilliant blue-white glow. Such intense radiation also drives a fierce stellar wind. Streams of charged particles blow off the star's outer layers, carrying the fury of its core out into space. It is humbling to remember that this very process is what makes all stars shine. The soft warmth of our Sun and the distant twinkle of the stars at night are powered by the fusion of hydrogen into helium deep in stellar cores. Every pinpoint of starlight in the night sky is a beacon of that energy, a reminder that across the universe, countless stellar furnaces are alight, turning matter into radiance. From our earthly vantage, the night sky's brilliance is a direct consequence of tiny amounts of mass being lost to energy in those cores at every moment, fueling the cosmos with light. Our massive star likely began its life in the company of others. Massive stars often form in clusters, alongside dozens or even hundreds of other young suns born from the same nebula. Within such a cluster, our star would have stood out brilliantly, a hot blue beacon among its smaller siblings. Its intense radiation may have blown away the remaining dust and gas of its birth cloud, carving a clear bubble in the nebula, as if announcing its presence to the cosmos. For a time, this hydrogen-fueled phase is relatively peaceful and enduring. In fact, it is the longest chapter in the life of any star, the main sequence, prime of life. Our massive star spends these millions of years steadily converting hydrogen into helium, radiating energy into the cosmos all the while. From an outsider's perspective, the star appears unchanging and eternal during this long stability. It shines with steady brilliance in the sky, a beacon of constant energy, while deep inside its core, the slow, patient transmutation of elements continues. Gradually, the helium ash of fusion accumulates in the core, even as the star outwardly shows no sign of the ongoing changes within. But even the most abundant fuel eventually runs low. After millions of years, the core's supply of hydrogen becomes exhausted. With fusion in the core faltering, the outward pressure that held gravity at bay begins to ebb. The star, once in comfortable balance, finds gravity forcing its core to contract again, heating up even further as it does. In this deepening heat, a new fire is about to ignite, one that will start burning the helium that has been piling up at the center. At last, the core becomes hot enough to kindle a new kind of fire. The inert helium that had been accumulating now turns into the star's fresh fuel. Helium nuclei, each containing 2 protons, require far more extreme conditions to fuse than hydrogen did. Yet under the crushing weight and rising heat of the contracting core, even these stubborn helium atoms begin to slam together. 2 helium nuclei collide, and for an instant form an unstable beryllium. If a third helium strikes during that fleeting moment, all 3 merge into a single carbon atom. This remarkable chain reaction, known as the triple alpha process, marks the start of the star's second great act of fusion. The triple alpha process is astonishing, not only in its power, but in its improbability. 2 helium nuclei can unite only very briefly into an unstable beryllium isotope. Normally, that beryllium would fall apart again almost instantly. Yet in the densely packed cauldron of the core, before it can decay, a third helium nucleus often crashes in, fusing all 3 into carbon. It is a rare 3-body collision made commonplace by the colossal number of helium nuclei flying about in the star's core. By sheer force of numbers, these unlikely reactions occur often enough to light a robust helium fire. In a star smaller than this, the onset of helium fusion can be a tumultuous affair. In sun-like stars, the core becomes electron degenerate, extremely compressed, before helium ignites, leading to a sudden helium flash when fusion finally begins. But in our massive star, the core remained a normal, non-degenerate gas, so helium burning starts gradually rather than explosively. The star smoothly settles into its new helium-burning life, brightening but not violently convulsing. No helium flash disturbs this giant star's transition. When this helium fire comes alive in the core of our massive star, it floods the core with a fresh wave of energy. The collapse of the core slows and then stops as the new source of pressure counteracts gravity once more. A shell of unburnt hydrogen just above the contracting core also ignites in response, forming a secondary fusion layer around the helium-burning center. Together, the helium-burning core and the hydrogen-burning shell pour out even more energy, and the star must adjust to this more intense furnace within. The star's response to this new energy is dramatic. Its outer layers swell outward, pushed by the increased internal pressure from the reignited core. As the star expands, its surface cools, and its color shifts into a rich orange-red hue. What was once a hot blue giant becomes a bloated red supergiant, hundreds of times larger in diameter than it was in its youth. If this star were at the center of our solar system, its swollen surface might extend beyond the orbit of Mars, perhaps even approaching Jupiter's path. This immense scale is comparable to that of Betelgeuse, the famous red supergiant in Orion. Although its surface is cooler and each square meter emits far less light than it did as a blue star, the star's total radiance remains undiminished. In fact, its luminosity can grow even higher because of its vastly expanded size. In this bloated state, the star's outer atmosphere is loosely bound by gravity. Some of the gas at the surface drifts away into space as a slow, steady stellar wind. The red supergiant may even pulsate, expanding and contracting gently over periods of years, each breathing cycle shedding a bit of material from the star's outer layers. Over time, the star becomes enveloped in a tenuous halo of its own lost gas, a glowing, circumstellar haze that is a prelude to the more violent shedding that will come later in its life. The metamorphosis of the star is profound. Once it was a compact blue-white beacon. Now it is an enormous crimson star, dominating its corner of the galaxy. Any planets that once orbited close to the star would have been engulfed by now, swallowed up as the star expanded. Even more distant worlds would find their skies filled by the star's vast red disk, and they would be scorched by the greatly increased luminosity. What was a brilliant blue giant in its youth has become a cooling but colossal supergiant in middle age, a star drastically changed in appearance and scale. A star in this red supergiant phase can also become somewhat variable. Its brightness might wax and wane gently over the years as the star's outer layers pulsate in and out. Sometimes a particularly large outflow of gas or a veil of newly formed dust can temporarily dim the star's light from our perspective, as happened during Betelgeuse's notable dimming observed in recent times. Such fluctuations are subtle foreshadowings of the star's unrest, signs that even in its majestic stability as a supergiant, change is always underway. For hundreds of thousands of years, the core continues to fuse helium into heavier elements. Every second, helium nuclei combine in threes, creating new carbon atoms and releasing energy to sustain the giant star. Some of the carbon that forms also fuses with additional helium, producing oxygen deep in the core. Gradually, a dense core of carbon and oxygen builds up at the center, elements that will one day serve as fundamental building blocks for planets and perhaps for life itself. The star remains alight and enormous during this time, held up once again by the power of fusion in its heart. Eventually, even the helium fuel is spent. The core, now filled with carbon and oxygen, finds itself without an energy source once more. Fusion in the center sputters out, and with nothing to push back against gravity, the core begins to contract yet again. Temperatures climb astronomically as the core shrinks in on itself, rising toward the next critical ignition point. Before long, the star's furnace will ignite yet another, even heavier fuel, the carbon at its center, to keep the fight against gravity alive a while longer. In whatever cluster or stellar family our star was born, it would now stand out dramatically. Many of its smaller, less massive sibling stars would still be in their prime, shining steadily as blue-white main sequence stars. Meanwhile, our massive star has raced ahead in evolution. It has swollen into a huge red supergiant that dwarfs and outshines those companions. It is a vivid demonstration of how a star's mass dictates its life's tempo. The heavyweight of the stellar family lives fast and transforms quickly, while its lighter siblings continue on a slower, steadier path. The cycle of collapse and rebirth continues as the star moves on to even heavier fuel. In the wake of helium depletion, the tightly compressed core finally grows hot enough for carbon fusion to begin. Now the carbon atoms that were forged from helium become the star's new energy source. Two carbon nuclei can slam together to form heavier elements, reactions that create neon and magnesium, among others, while releasing a burst of energy. Carbon burning is fiercer and more short-lived than the stages before it. But for a time, it gives the star a new lease on life. From this point onward, the star will race through a succession of new fuels in quick order. Each stage of fusion requires a higher temperature and pressure than the last. As a result, each fuel is consumed more rapidly than the previous one, and the star's life accelerates toward its finale. By this point, the star's interior has developed a rich, layered structure, like the layers of an onion. While carbon fuses in the core, shells of the earlier fuels continue to burn around it. Just above the carbon-burning core, a shell of helium still fuses into carbon. Beyond that, a shell of hydrogen continues fusing into helium. Each layer generates energy, contributing to the star's luminosity and helping support the weight of the enormous star. With each successive stage, another shell of fusion is added to this cosmic onion. Later on, shells burning neon, oxygen, and even silicon will join the stack, nested one inside another. The once simple star has become a complex tapestry of concentric fusion zones, each one burning a different element. Our massive star is itself part of a larger cosmic story of element creation. The heavy elements that enabled its hydrogen fusion, those carbon, nitrogen, and oxygen atoms serving as catalysts, were forged in stars that lived and died long before our star was born. In that sense, this star carries the inheritance of earlier generations of stars. Now, in its own core, it is adding to that legacy, creating new heavy elements that will one day be scattered into space for future stars and planets to incorporate. Inside the carbon-burning core, a variety of nuclear reactions take place. When two carbon nuclei fuse, one common outcome is that they form an isotope of neon and release a leftover helium nucleus. In other instances, carbon fusion can produce elements like sodium or magnesium. The exact products vary, but the trend is clear. The star is forging elements heavier than carbon for the first time, enriching its core with an assortment of new atomic treasures. But carbon, too, is only a temporary reprieve. In a matter of mere centuries, the core's carbon fuel is exhausted, leaving behind a growing concentration of neon, oxygen, and magnesium created in those final burning reactions. Once again, the core begins to collapse under gravity's unrelenting pull. As the core compresses further, temperatures soar into the billions of degrees. Before long, neon, one of the products of carbon burning, ignites as a new fuel. Neon fusion in the core generates yet more oxygen and magnesium, releasing energy in another brief burst that holds gravity at bay for a short while. Neon burning actually proceeds through a slightly different route than the earlier stages. The core becomes so energetic that neon nuclei start to be bombarded by gamma rays and break apart. Some neon atoms split into an oxygen nucleus and a helium nucleus, and those freed helium nuclei then fuse with other neon nuclei to form magnesium. In this indirect way, neon is consumed, yielding more oxygen and magnesium in the core, and providing another short-lived infusion of support to the star. The pattern repeats with increasing urgency. Neon fuel is spent in perhaps just a year or two before the core again runs out of steam. Each time a fuel is exhausted, the core resumes its collapse until the intense heat and pressure spark the next reaction. After neon, it is oxygen's turn. In the raging furnace of the contracting core, oxygen nuclei smash together and fuse, forging elements like silicon and sulfur in the process. Oxygen fusion pours out tremendous energy, but it, too, is a fleeting stage in the star's life, lasting maybe only a few months before its fuel is gone. Now the star is down to the last fuel it can burn. With oxygen gone, the core is left rich in silicon and sulfur, the next seeds for fusion. Gravity forces the core into one more round of contraction, driving temperatures to astonishing heights of roughly 3 billion degrees. At this point, silicon nuclei in the core begin to fuse. Through a chain of rapid reactions, silicon fusion produces elements clustered around iron on the periodic table. Mostly iron itself, along with nickel and cobalt. This final burning phase is the most intense yet, but it is also heartbreakingly brief, lasting perhaps only a day or two before every last bit of silicon fuel is expended. After this furious sequence of elemental alchemy, the star has forged as heavy a core as nature will allow through normal fusion. At the heart of the giant now lies a dense core made mostly of iron, the end product of silicon burning. Unlike all the fuels that came before, iron brings no further energy when it fuses. It is the one element the star cannot use to stoke its furnace. In a sense, the star has climbed as high as it can on the fusion ladder, and there are no more rungs left to burn. Remarkably, from an external viewpoint, the star still appears much as it has throughout its supergiant phase. No obvious sign betrays the turmoil within. The red supergiant continues to shine placidly. Its vast crimson surface might only show gentle pulsations, giving little indication that deep inside, an iron heart has formed, and the star is living on borrowed time. The final catastrophe is brewing in secret, while to the outside universe the star remains a picture of stately, ancient splendor. The star has now reached an impasse. Its core is filled with iron. What does this mean for the star's fate? Iron is a special and final element in the life of a star. Unlike hydrogen, helium, or even silicon, fusing iron does not release energy. In fact, it consumes energy. In the hierarchy of atomic nuclei, iron sits at the peak of stability. It has the most tightly bound nucleus of them all. That means if you try to force iron atoms to fuse into something heavier, or even split them into something lighter, they stubbornly refuse to yield any net energy. For a star's core, this is a dead end. Iron is essentially the ash of the star's nuclear furnace, an element that simply will not burn. And so, as silicon burning rages, and the star's multiple shells keep fusing lighter elements, the iron ash in the core continues to pile up. The core grows into a dense iron ball, extremely hot, on the order of billions of degrees, and incredibly compact. Yet no matter how hot it gets, it cannot ignite iron to produce any further support for the star. For a short while, the iron core simply sits there, sustained only by the pressure of its tightly packed electrons, pushing back against gravity. But this stalemate cannot last forever. By the time silicon burning is complete, the iron core is enormous by terrestrial standards, yet tiny compared to the whole star. It is roughly the size of Earth in diameter, but contains nearly 1.5 times the mass of our Sun packed into it. This iron heart is unbelievably dense and searingly hot. Its temperature climbs above 1 billion degrees, and its density rivals that of a white dwarf star. For the moment, it is held up only by the quantum pressure of electrons crammed together in its volume, a manifestation of what physicists call electron degeneracy pressure. With each passing moment, more iron is added to this core by the burning shells above it. The iron core grows more massive, and as it does, its ability to support itself slips away. There is a critical point, a tipping mass, approximately about 1.5 times the Sun's mass, beyond which the core can no longer hold up under its own weight. When that threshold is reached, gravity wins decisively. In a fraction of a second, the iron core begins to implode inward. What follows is a catastrophic collapse unlike anything the star has experienced before. The implosion occurs in the blink of an eye. In under a second, the core contracts violently, with matter hurtling inward at a significant fraction of the speed of light. As the core implodes, its temperature soars to levels that cause iron nuclei to break apart. High-energy gamma rays slam into the iron nuclei and shatter them into smaller pieces, effectively undoing all the fusion that created them. This reversal of fusion absorbs energy, draining heat from the core and accelerating the collapse even more. Electrons are forced into protons, turning them into neutrons, and flooding the core with neutrinos that stream outward at nearly the speed of light. In mere moments, the core's matter is crushed to a density comparable to that of an atomic nucleus. The entire core, once roughly the size of a planet, is now squeezed into a sphere only a few tens of kilometers across. At last, the collapse grinds to a halt when the core matter can be compressed no further. Like a spring suddenly uncoiling, the inner core rebounds ever so slightly as it slams into this wall of nuclear density. Infalling layers crash into the unyielding core and ricochet outward in a titanic shockwave. In that fleeting instant, the star's core has transformed into something new, a super-dense ball of neutrons, in effect, a newborn neutron star, and it pushes outward with enormous force. The energy released in the core collapse is almost unimaginable. In that brief instant, more energy floods out of the core, mostly in the form of neutrinos, than the star radiated over its entire millions of years of life. This titanic burst of energy is what powers the shockwave now racing outward, poised to blow the star apart. Even space and time themselves shudder from the core's convulsion. Subtle gravitational waves ripple away, carrying news of the collapse across the cosmos. When a real massive star's core collapsed in 1987 in a nearby dwarf galaxy, an event known as supernova 1987A, astronomers on Earth detected a sudden burst of neutrinos, direct evidence that such a collapse was taking place deep inside before the star exploded. It was as if we briefly glimpsed the star's dying heartbeat through those ghostly particles flooding out. For a few milliseconds, the collapse has been halted and reversed. A powerful shockwave is now surging outward from the core. The long struggle between pressure and gravity has ended in the core's defeat. Gravity has finally, utterly prevailed. The star is on the brink of an irreversible transformation. The collapse of its core is the final, decisive turn in this cosmic tug-of-war, and it will soon lead to the star's spectacular demise. Throughout all these stages of stellar evolution, an invisible dance has been taking place in the heart of the star. Even our sun is quietly maintained by this same balancing act. On one side is gravity, ever pulling the star's mass inward, trying to crush the core. On the other side is pressure generated by the star's internal heat and the flood of radiation from fusion, pushing outward. For most of the star's life, these two forces held each other in a delicate balance, maintaining the star's stability through the long epochs of hydrogen and helium burning. When the star's core is steadily fusing its fuel, it naturally settles into this equilibrium. If the core produces even a bit too much energy, the extra pressure causes the star to expand slightly, which in turn cools the core and slows the fusion reactions. Likewise, if fusion falters and the pressure drops, gravity makes the core contract and heat up, which boosts the fusion rate again. This self-regulating cycle keeps the star on an even keel, like a tightrope walker, making constant tiny adjustments to stay balanced. However, the balance is not permanent. Each time a fuel in the core runs out, the outward pressure that held gravity in check begins to fade. Gravity seizes that moment to tighten its grip, and the core starts to shrink until a new source of pressure, the next fusion reaction, can ignite. These transitions are times of upheaval for the star. The core contracts and heats, the surrounding layers respond, and often the star's outer appearance changes dramatically as it adapts to a new equilibrium. We saw this happen when the star finished burning hydrogen in its core. With the core temporarily out of fuel, gravity drove a contraction that raised the internal temperature, which then ignited helium. The star responded by establishing a new balance, helium burning in the core and hydrogen burning in a shell, which caused the outer layers to swell into a red supergiant. At each new stage, the star found a different equilibrium configuration, but always the same tug-of-war continued deep inside, gravity squeezing inward, and radiation and thermal pressure pushing outward. In the final act, when the core turned to iron, this grand balancing act finally tipped irrevocably in gravity's favor. With no more energy to be gained from fusion, the outward pressure in the core died away. For the first time, there was nothing to oppose gravity's crush. The result was the catastrophic collapse of the core, an outcome far more sudden and violent than any adjustment that came before. Gravity, the ever-present force that had patiently waited, finally overwhelmed the star's last defenses. This collapse of the core is not like the gentle self-corrections of earlier times. It is sudden, final, and it heralds the star's spectacular end. For eons, the star's very existence was defined by this balance between gravity and pressure. But now that equilibrium has been decisively broken. The core's collapse marks the ultimate victory of gravity in this long contest. With nothing left to uphold the star, its destruction is imminent, a violent end to the majestic stability it maintained for so long. Massive stars, like the one we've been following, are the sprinters of the cosmos. They live their lives at a breakneck pace, burning through their nuclear fuel far more quickly than smaller stars. In fact, a star with 10 times the sun's mass might shine thousands of times brighter, so despite having vastly more fuel, it uses that fuel far faster. The greater a star's mass, the greater its internal gravity and pressure, which means its core burns hotter and more fiercely. This intense furnace consumes fuel ravenously, causing the star to shine with immense power, but also to age at an accelerated rate. Massive stars, such as this, are relatively rare. Only a tiny fraction of all stars in the universe are born with such extreme mass. The majority of stars are far smaller and fainter. Yet despite their scarcity, massive stars have an outsized influence on their surroundings. They dominate the light of their stellar communities and are crucial for enriching the cosmos with heavy elements. In cosmic terms, being bigger and brighter means living fast and dying young. It is a cosmic irony that although a massive star begins life with far more fuel than a smaller star, it runs out of that fuel much sooner. Our Sun, a medium-mass star, will shine on hydrogen for roughly 10 billion years. But a star dozens of times more massive might exhaust its core hydrogen in only a few million years. An even smaller star, a cool red dwarf, sips its fuel so slowly that it can last for hundreds of billions or even trillions of years. Thus, in the stellar realm, greater mass truly comes at the price of a shorter life. Despite their short lives, massive stars shape the universe in significant ways. During their brief existence, their intense radiation and strong winds stir and sculpt the surrounding interstellar gas. They often form in clusters, carving huge bubbles in the nebulae with their energetic outflows. And when they die, they dramatically seed their galactic neighborhood with newly forged elements, leaving a lasting chemical legacy long after the individual star is gone. It's worth noting that only the most massive stars meet such spectacular ends. Lower mass stars, like our Sun, live far longer and die much more quietly, never reaching the conditions needed for an iron core collapse. The Sun, for example, will expand into a red giant and then shed its outer layers gently, leaving behind a dense core, a white dwarf, but no supernova explosion. Our massive star, by contrast, has no such gentle finale. Its destiny is to perish in a blaze of glory. In our massive star's case, the tempo of life speeds up drastically with each successive fuel. Its hydrogen-burning youth may have lasted on the order of 5 million years. When that was over, its core fused helium for perhaps only a few 100,000 years. After helium, the carbon-burning stage might have endured for mere centuries. Neon burning could flash by in a year or less, and oxygen fuel would be spent in only a few months. By the time the star ignited its final fuel, silicon, the clock was ticking in days. The end was truly near. It is as if the star's internal clock speeds up with each new fuel, racing toward the final midnight of its life. This acceleration toward the end is so extreme that on human or even planetary timescales, it is almost inconceivable. A star that maintained a near constant appearance for millions of years can be thrown into its final crisis and meet its end practically overnight. The changes in the core happen so fast that the star's outer layers barely have time to react. To an outside observer, there would be almost no warning in the star's outward appearance of the catastrophe about to unfold, until the very moment it does. After such a brief, blazing life, the massive star now stands at the brink of death. With its core spent and collapsed, all that remains is the star's final act, a last, titanic release of energy that will tear the star apart. In a supernova explosion, more luminous than billions of suns, the star will blaze for a few weeks with unbelievable brilliance, outshining entire galaxies. In that moment, all the heavy elements forged during the star's life will be hurled into space, seeding the interstellar clouds with the ingredients for new stars, new planets, and perhaps even new life. In dying, the star will kindle the birth of new worlds to come, continuing the cosmic cycle of creation. The clock has nearly run out for our massive star, and the era of fusion in its heart has ended. What comes next will be the grand finale of this stellar tale. Deep within the massive star, a profound change is underway. For millions of years, this stellar giant has burned brightly, fusing lighter elements into heavier ones and holding collapse at bay. But now, its once fierce furnace is exhausted. The core is filled with iron, a dead end for fusion, from which no energy can be squeezed to fuel the star's resistance against gravity. At this final stage, the star itself has swollen to monstrous proportions, becoming a bloated red supergiant. If this dying star were placed at the center of our solar system, its surface might extend beyond the orbit of Mars, engulfing the inner planets. Despite its immense size, the star's outer layers are tenuous and cool, while deep inside the core continues to contract and heat. The once steady glow has turned unstable and flickering, a sign that the star is poised on the brink of catastrophe. With no new heat to push outward, the balance holding the star in equilibrium begins to falter. Outward pressure fades, and the inward pull of gravity gains the upper hand. In the core's deep interior, atoms are crushed together as the weight of the overlying layers bears down. The star's heart begins to contract, slowly at first, then ever more rapidly as nothing remains to stop the imploding force. As the core contracts, temperatures and pressures soar to unimaginable extremes. In a matter of seconds, the collapse goes from a steady squeeze to a catastrophic plunge. The core, once a sphere roughly the size of Earth and loaded with a mass comparable to our Sun, crumples inward violently. Within a heartbeat of cosmic time, it shrinks from thousands of kilometers across to barely tens of kilometers, hurtling inward at a significant fraction of the speed of light. At these crushing densities, exotic processes erupt. Atomic structure itself fails under the immense gravity. Protons and electrons, normally kept apart, are slammed together and merge into neutrons. In the blink of an eye, the core transforms into an ultra-dense ball of neutrons. A flood of nearly invisible particles called neutrinos bursts out from this mayhem, carrying away energy from the imploding core. Trillions of these ghostly neutrinos stream through the collapsing star and race outward into space. For a brief moment, the collapsing core becomes as dense as an atomic nucleus. Then, abruptly, the implosion grinds to a halt. The neutrons in the core can be compressed no further. They resist with a powerful degeneracy pressure, an unyielding stiffness of nuclear matter. The inrushing material slams into this newly unbreakable neutron core as if hitting a solid wall. In that instant, the core rebounds, a ferocious, tiny recoil at the center of the star. This sudden rebound sends a powerful shockwave surging outward. A titanic pressure front now plows through the infalling layers that were still rushing inward. The shock struggles to propagate. It is slowed at times by the star's heavy overlying layers, but it is revved up by the vast energy pouring out of the core. Those countless neutrinos, though ghostly, deposit a fraction of their energy into the surrounding matter, revitalizing the outward-moving blast. Now a massive shockwave is tearing its way up through the star's interior. In mere seconds, it traverses thousands of kilometers, ripping through layer after layer of silicon, oxygen, carbon, helium, and hydrogen that the star had built up in onion-like shells. All the while, it gathers momentum and strength. The star's fate is sealed. Its core has collapsed and rebounded, and nothing can stop the eruption that is about to unfold. Moments later, the star's surface can no longer contain the turmoil raging within. The shockwave reaches the star's outer layers and explodes forth into space. In one stupendous instant, the star's entire outer shell is blown away. What was once a stable, shining star is now a rapidly expanding fireball, an explosion of unimaginable grandeur. The dying star has become a supernova. The supernova erupts with a brilliance that defies comprehension. For a short time, this single exploding star outshines all the billions of stars in its galaxy. It is as though a new star, brighter than anything seen before, has appeared where the massive star once lived. The night sky around the star's host galaxy is flooded with its radiance. From across vast distances, observers would see a sudden beacon, a star that wasn't there before, shining with ferocious intensity. Such stellar death throes are as beautiful as they are violent. The explosion's light can rival the glow of an entire galaxy, and it can persist for weeks or even months. Astronomers on Earth, even in distant future generations, could witness the spectacle with the naked eye if the star is relatively nearby. In some cases, a supernova in our own galaxy can burn so brightly that it becomes visible even during the day. It is a cosmic firework display on the grandest scale, a final glorious flourish marking the end of the star's life. For an observer at a safe distance, watching a supernova unfold is both awe-inspiring and eerie. At first, the star suddenly surges in brightness, turning into a beacon where none had been before. On subsequent nights, its brilliance may subtly change hues, a bluish-white glare at peak intensity, then a golden tint, and finally a fading crimson as the ejected gases cool and expand. What was once a single pinpoint of light might grow into a tiny visible cloud when seen through a telescope, as the star's remnants spread outward. After weeks of spectacle, the light eventually wanes. In the patch of sky where a mighty star once shone, there remains only darkness to the naked eye, and perhaps a faint, ghostly nebula visible only with powerful instruments. History bears witness to these celestial fireworks. Over the millennia, humans have occasionally seen stars explode in our sky. In the year 1006, observers from Europe to East Asia recorded a brilliant new star that lit up the night, casting shadows and even appearing in the daytime sky. A few decades later, in 1054, skywatchers in China and elsewhere noted another guest star that mysteriously burst into view. It shone so brightly that for weeks it could be seen even in daylight, and at night it cast eerie shadows on the ground. Unbeknownst to those ancient observers, they were witnessing a supernova, the death throes of a distant star. Its ghostly remnant, the Crab Nebula, still glows in the sky today, a testament to that long-ago stellar explosion. There have been other such sightings. In 1572, the Danish astronomer Tycho Brahe was astonished by a brilliant new star that suddenly appeared in Cassiopeia and remained visible for many months. Just 3 decades later, in 1604, the astronomer Johannes Kepler marveled at another nova that lit up the sky in Ophiuchus, shining for weeks before slowly fading over the following year. In 1987, modern astronomers observed a supernova in a nearby galaxy, the brightest seen in nearly 4 centuries. Neutrino detectors deep underground even registered an ethereal burst of particles from that distant blast, heralding the explosion just before its light reached Earth. Each of these events was a massive star ending its life in a sudden blaze of brilliance. Supernovae in any one galaxy are relatively rare, perhaps only a few per century in a galaxy like our Milky Way. Yet across the cosmos as a whole, they are common events. With trillions of galaxies, each hosting billions of stars, somewhere a star explodes every moment. In fact, by some estimates, a supernova may occur somewhere in the observable universe nearly every second. We on Earth glimpse only a tiny fraction of these distant stellar cataclysms, but they are a continuous and essential part of the universe's unfolding story. As awe-inspiring as these historical supernovas were, the sky may yet have more fireworks in store. One star in particular, the red supergiant Betelgeuse in the constellation Orion has captured astronomers' attention as a potential future supernova. In recent years, Betelgeuse has dimmed and brightened unpredictably, sparking speculation that it could explode within our lifetimes, though it might be decades or millennia before it truly goes, and no one can be certain. If Betelgeuse were to go supernova, it could shine brighter than the full moon, turning night into a dim daylight for weeks on end. Fortunately, at around 640 light-years away, it poses no threat to Earth. But it would dazzle our skies like nothing seen in recorded history, a vivid reminder that the drama of stellar death is still unfolding in our galaxy. Amid all the brightness and spectacle, the supernova is doing more than putting on a show. In the heart of the explosion, a kind of cosmic alchemy is occurring. The extreme heat and pressure of the blast drive nuclear reactions that were impossible in the star's quieter days. As the star's guts are hurled outward, atoms slam into each other and capture stray neutrons, forming heavier and heavier elements. In mere seconds, elements that took eons to form inside the star, and elements that could never form there at all, are synthesized in the furious crucible of the supernova. Before the explosion, the massive star had already created a rich inventory of elements during its lifetime. Deep in its core, it fused hydrogen into helium, helium into carbon and oxygen, and onward to neon, silicon, and finally iron. But it stopped at iron, the end of the line for energy-producing fusion. Now, in the supernova's upheaval, that limit is shattered. The enormous shockwave and the flood of neutrons and neutrinos provide the energy and particles needed to build elements heavier than iron. In this brief stellar apocalypse, gold and silver are forged, as are iodine, uranium, and dozens of other rare heavy elements. The star's death throes become an assembly line for some of the most precious materials in the universe. All those newly formed atoms, along with the elements the star forged during its life, are flung into space by the explosion. The debris of the supernova is no mere smoke and ash. It is a treasure trove of elemental riches. Great clouds of glowing gas billow outwards, carrying the carbon that will form future diamonds, the oxygen that will fill the lungs of living creatures, and the silicon that will one day congeal into rocky planets. The contents of that shattered star will mix and mingle with the interstellar medium, enriching it with the raw materials for new worlds. In fact, astronomers have been astonished by the sheer quantities of elements a supernova can produce and disperse. One exploding star can forge and hurl out more iron in a few moments than the Earth contains over its entire lifetime. It can likewise send vast stores of oxygen, carbon, and other crucial elements flying into space, material that will become the building blocks of future stars, planets, and perhaps life. These mind-boggling numbers highlight how thoroughly supernovae enrich the cosmos. In this way, supernovae are the universe's master chemists and generous benefactors. Each exploding star spills its inner wealth into the galaxy, ensuring that later generations of stars will be born from gas that is not just hydrogen and helium, but seasoned with heavier elements. Without these titanic explosions scattering elements far and wide, the cosmos would lack many of the ingredients that we on Earth find familiar. There would be no iron for blood, no calcium for bones, no carbon for life's complex molecules. Planetary worlds like our own might never have formed in the rich, diverse way that they did, filled with minerals and materials essential for living organisms. It's often said that we ourselves are made of star stuff, and this is no poetic exaggeration. It is quite literally true. The atoms that compose our bodies were forged in ancient stars and spread through space by stellar explosions. Long before our sun existed, an earlier generation of massive stars lived and died, bequeathing the iron in our blood and the calcium in our teeth. Every breath we take contains oxygen that was cooked up in the core of a massive star and blown into interstellar space by a supernova. In a very real sense, we carry the legacy of long-dead stars within us. As the supernova debris expands and cools over thousands of years, it gradually blends into the surrounding sea of gas between the stars. The heavy elements will become part of immense cosmic clouds. In time, under the gentle pull of gravity, those clouds may begin to collapse and fragment, forming new stars and new planets. Thus, in the ashes of a dead star lie the seeds of new suns. The cycle of star birth, death, and rebirth is written into the chemical abundances of the galaxy. The catastrophic ending of one star becomes the hopeful beginning for countless others. Yet, amid the ejected debris of the supernova, something of the star itself remains. The core, transformed by the collapse. What has become of that crushed heart that triggered the explosion? While the outer layers sail away enriched by newly forged elements, the star's core has undergone its own dramatic rebirth in disguise. Often it emerges as a neutron star, a city-sized ember of ultra-dense matter spinning amid the wreckage. Our journey now turns to that strange remnant left behind in the aftermath of the blast. At the center of the expanding wreckage, a tiny but extraordinary object is born from the star's demise. This is the neutron star, the ultra-dense core left after a supernova, no larger than a city, yet more massive than the sun. It is a stellar corpse, a collapsed core composed almost entirely of neutrons. In the aftermath of the supernova's fury, all the star's remaining mass has crushed itself into this compact ball. To grasp a neutron star's scale, imagine shrinking the sun to the size of a city, perhaps 20 kilometers across. All that mass, squeezed into a sphere only a few tens of kilometers wide, creates a density that defies ordinary understanding. A single teaspoon of neutron star material would outweigh a mountain, billions of tons compressed into a few cubic centimeters. The gravity at its surface is unimaginably strong, hundreds of billions of times stronger than Earth's gravity. If we could somehow stand on such a surface, an impossibility of course, we would be instantly crushed flatter than a sheet of paper by our own weight under gravity's relentless pull. Newly born from collapse, neutron stars are incredibly hot and brimming with energy. They typically spin at dizzying speeds, a consequence of the parent star's core rotation being conserved and vastly amplified as it shrank. A neutron star may rotate dozens or even hundreds of times per second, turning faster than a kitchen blender's blade. As it spins, intense magnetic fields, trillions of times stronger than Earth's field, funnel charged particles into beams that shoot out from the magnetic poles. If these beams sweep past Earth, we detect pulses of radiation at regular intervals, like the flashing of a cosmic lighthouse. Astronomers call these rapidly blinking neutron stars pulsars. The discovery of pulsars was one of the great surprises of modern astronomy. In 1967, a young scientist named Jocelyn Bell noticed a peculiar signal, a steady blip of radio waves pulsing every 1.3 seconds with uncanny regularity. For a brief time, she and her colleagues half-jokingly dubbed the source LGM1 for Little Green Men, teasing the possibility of an alien beacon. But it soon became clear that this was not extraterrestrial intelligence at work, but something even more astonishing, a rapidly spinning neutron star emitting lighthouse-like beams. The first pulsar had been found, confirming that neutron stars, predicted by theorists decades earlier, were not just theoretical objects. They were real, and they were out there, flashing in the cosmic darkness. Since that landmark discovery, astronomers have found hundreds of these pulsating neutron stars scattered throughout our galaxy. They vary in their speeds and intensities, but all shine as incredibly regular beacons. Some spin at truly mind-boggling rates, hundreds of rotations each second, their beams flickering like cosmic strobe lights. These fast pulsars serve as astonishingly precise clocks in space, allowing scientists to test the laws of physics under conditions we cannot replicate on Earth. Neutron stars push physics to its limits. Matter in their cores is compressed beyond anything found elsewhere. Atoms themselves can no longer exist as separate entities when crushed together so tightly. Instead, the star is essentially one gigantic atomic nucleus, made mostly of neutrons. The behavior of matter at these densities is still not fully understood. Deep inside a neutron star might lurk exotic states of matter, perhaps an ocean of free quarks or other particles squeezed out of their usual confines. The crust of the star is equally extreme, a solid lattice of nuclei and electrons, and a mere fragment of that crust, if somehow brought to Earth, would outweigh entire mountains. Occasionally, neutron stars can undergo sudden internal adjustments called starquakes, a violent cracking of their crust as it settles and shifts. When that happens, the neutron star can release a burst of X-rays or gamma rays, flaring up momentarily. Some neutron stars are magnetars, possessing magnetic fields so ferocious that they can distort the very atoms on the star's surface. Magnetars have been known to unleash giant flares of radiation that momentarily outshine even their own supernova remnants, sending showers of high-energy particles across space. These exotic behaviors add to the mystique of neutron stars, making them one of the most fascinating end states of stellar evolution. For all their power, neutron stars are also somewhat ghostly and elusive. A lone neutron star, unless it's a pulsar beaming toward us, can be incredibly difficult to detect. A tiny, cooling ember fading in the darkness. It might simply drift amid the silent void, its hot surface emitting mostly X-rays and gradually dimming over millennia. Yet, if a neutron star has a close companion, its intense gravity can pull gas off the neighboring star, heating that gas to millions of degrees. Such infalling matter can light up the neutron star's surroundings in X-rays, briefly announcing the neutron star's presence. In some quiet corner of the galaxy, countless neutron stars likely wander invisibly, like scattered ashes from old cosmic fires, awaiting discovery by our telescopes. Still, there is a limit to what even these dense objects can endure. The neutron star is a final refuge against gravity's onslaught, but only up to a point. If the original star was even more massive, the core remnant might exceed the weight that neutrons can support. Beyond that threshold, gravity's victory becomes absolute. The stellar remnant will collapse further, shrinking beyond the neutron star stage. In cases where the star that died was truly colossal, the aftermath is even stranger than a neutron star. When an immense core collapses with no force in nature able to halt it, a black hole is born. This is gravity's final and most audacious act. Matter crushed so completely that nothing can escape its grip, not even light. The core that once shone as the heart of a star is transformed into a region of pure darkness, an invisible pit in spacetime itself. The newly formed black hole announces itself only by its gravitational pull. The star's remaining mass, along with any nearby gas, will swirl into the black hole's grasp, heating up and emitting powerful X-rays and gamma rays in the process. In the chaotic moments during and after the collapse, the black hole might produce narrow jets of energy that shoot out along its poles, piercing through the wreckage of the star, some of the brightest bursts of energy ever recorded, brief gamma-ray bursts, are thought to mark the birth of a black hole in the collapse of a massive star, momentarily outshining everything else in the universe. For any object unfortunate enough to venture too close to a black hole, the difference in gravity between its near side and far side becomes overwhelming. The object would be stretched apart along its length and compressed from the sides. A gruesome distortion aptly dubbed spaghettification by astronomers. A star, a planet, or anything else that falls in meets this fate, pulled into a long, thin shape as it spirals inward. Ultimately, it is torn to pieces and vanishes beyond the event horizon, lost to the rest of the universe. Yet, a newborn black hole itself emits no light. It is a silent darkness where the star's core once resided, a gravitational presence without a visible form. If the black hole is left alone in space, even the brilliant fireworks of the supernova will eventually fade around it, and it will settle into obscurity, detectable only by its gravitational effects on the environment. It's awe-inspiring to consider that a massive, roaring star can end its life as a quiet hole in the universe, a patch of curved space-time where matter and light simply disappear. Black holes were once purely theoretical, conjured by equations and thought experiments long before we had evidence they existed. But nature has confirmed their reality in spectacular ways. At the center of our Milky Way, astronomers have tracked stars whipping around an unseen object with about 4 million times the Sun's mass, our galaxy's central black hole, whose gravity yanks those stars in rapid orbits. In 2015, instruments on Earth detected gravitational waves, faint ripples in spacetime, from the distant merger of two stellar mass black holes, a signal of a colossal collision that happened billions of years ago. And in 2019, an international team of scientists unveiled the first ever image of a black hole's silhouette, a glowing ring of gas silhouetting the darkness of a supermassive black hole in a galaxy 55 million light-years away. These breakthroughs have made black holes, once abstract ideas, into tangible cosmic phenomena that we can observe and study. In the context of our dying massive star, if enough mass fell back into the core after the supernova explosion, a black hole could form right there amid the chaos. In some instances, a star might even collapse directly into a black hole without a visible supernova at all, quietly winking out of sight instead of going out with a bang. Imagine a star that shone brightly for millions of years, and then, in an instant, it's gone. A dark mystery where once there was light. This silent, failed supernova collapse is rare and hard to catch in the act, but astronomers have found hints that such events do happen in our universe. Whether formed with a brilliant explosion or in utter silence, a black hole is gravity's ultimate triumph over matter. It is literally a hole in the universe, a gravitational trap from which neither matter nor light can return. Over time, the newborn black hole might gulp down the surrounding debris of the explosion, or remain quietly embedded in an expanding shell of gas that was once the star's outer layers. Either way, what was once the star's core has now become something almost beyond comprehension, an object so extreme that it swallows light and time itself. Yet, the story of our star's death is not quite finished. Though the core has met either the exotic fate of a neutron star or the even stranger fate of a black hole, the legacy of the star still expands outward in the cosmos. The spectacular supernova has strewn the star's outer layers into space, creating an ever-growing nebula of stellar debris. It is to this drifting ghost of the star that we now turn. The beautiful, eerie remains that persist long after the initial blast has faded away. Long after the flash of the supernova has dimmed, the aftermath of the explosion continues to evolve. What remains of the star spreads out into the surrounding space as a vast, expanding cloud. This cloud, the supernova remnant, is the delicate shell of glowing gas and dust that once made up the star's outer layers. It drifts through the galaxy like a ghost of the star, an ethereal remembrance of the explosive event that ended its life. In the early years after the explosion, the remnant is unimaginably hot and bright, a bubble of searing plasma. Shock waves from the blast race ahead of it, heating interstellar gas to millions of degrees. As the decades and centuries pass, the remnant expands and cools, and intricate filamentary structures begin to emerge. Through telescopes, these remnants appear as beautiful wisps and ribbons of light, tenuous filaments and knots glowing against the darkness. They come in many shapes. Some remnants form nearly spherical shells. Others are shattered into asymmetric webs. Each one is sculpted by the details of the star's explosion and by the environment into which it expands. Every supernova remnant carries the unique signature of its progenitor star's death. The composition of the gas tells the tale of what elements were created and ejected in that final blast. Astronomers, by studying the light from these remnants, can identify the fingerprints of specific atoms, perhaps the red hue of hydrogen, the green of glowing oxygen, or the purple-blue of ionized sulfur and silicon. By mapping the distribution of these elements in the expanding cloud, scientists can reconstruct the star's final moments. Like forensic investigators at a cosmic crime scene, they piece together how the explosion unfolded, deciphering, for instance, whether the star blew off its layers evenly or in jets, and which parts of the star ended up where in the remnant. In this way, each remnant is a kind of autopsy report of the star that died, preserving details that the star's light alone could not have told us. Some of the most famous supernova remnants have become icons of cosmic beauty and scientific intrigue. The Crab Nebula, left behind by the supernova of 1054, is a tangled web of filaments energized by a pulsar still beating at its center. Its filaments glow with a rich palette of elements, crimson from hydrogen and emerald from oxygen. The entire nebula continues to expand outward at thousands of kilometers per second, propelled by the energy of the long-ago blast. In another part of our galaxy lies Cassiopeia A, the remnant of a star that exploded around the 17th century. Through modern telescopes, Cass A appears as an uneven ring of gaseous clumps. Jets of debris hint at a possibly off-kilter explosion. Each color in its X-ray image corresponds to a different element, painting a picture of how the star's innards were hurled apart. Elsewhere in the cosmos, an older supernova remnant called the Veil Nebula offers a more delicate spectacle. This faint, lace-like cloud in the constellation Cygnus is all that remains of a star that exploded thousands of years ago. Its gossamer filaments of gas stretch across dozens of light years, glowing softly in hues of red and blue, a web of cosmic silk draped against the starry sky. Even in its quiet old age, the Veil Nebula whispers of the violence that created it, a beautiful echo of a long-faded stellar cataclysm. These ghostly remnants serve as laboratories for astrophysics long after the star is gone. Within their expanding shells, particles are accelerated to near the speed of light by the explosion's shock waves, creating cosmic rays that will wander the galaxy. Indeed, scientists now know that many of the high-energy cosmic rays zipping through space, some of which rain down on Earth, are spawned by supernova remnants. The glowing filaments remain extraordinarily hot, shining not just in visible light, but in X-rays and radio waves that astronomers can study to understand the physics of shock waves and heated plasma. Over thousands to tens of thousands of years, the supernova remnant will continue to spread out, eventually blending into the general interstellar medium. In some cases, the shock front from the explosion may ram into nearby molecular clouds and trigger new stars to form, seeding the next generation of stellar life. In fact, some evidence suggests that a supernova's shockwave might have helped trigger the birth of our own sun over 4.5 billion years ago. The sight of a supernova remnant is a reminder that even in death, a star influences its cosmic neighborhood profoundly. The patterns we observe in those wispy filaments and expanding clouds are cosmic fingerprints, unique identifiers of the star's life and explosive end. No two supernova remnants are exactly alike. Some are nearly spherical bubbles, others ring-like, others fragmented and chaotic. Their differences encode information about the star's mass, its rotation, whether it shed layers before it exploded, and how the blast wave tore through the star's interior. By examining these differences, astronomers can decode the story of each stellar detonation and better understand the diverse ways in which massive stars can meet their end. Eventually, as the millennia pass, the glowing gases of the remnant will cool and dim, and the structure will gradually dissipate. The individual identity of the supernova remnant will fade as its material merges into the surrounding interstellar medium. The elements and gases from that remnant, the oxygen, carbon, iron, and more, will drift through space, perhaps to be swept up in new cosmic clouds. In this way, the remains of the star become part of the raw material for new stars and planets. The cycle continues. The end of one star becomes a contribution to the beginnings of others. Our massive star's journey has reached its end, a spectacular cataclysm that has destroyed the star, yet scattered the seeds of new beginnings. In the silent aftermath, a faint nebula, and perhaps a tiny neutron star, or an invisible black hole, are all that mark the spot where a brilliant sun once shone. The once mighty star is gone, but its influence echoes through the surrounding space. The shockwave and debris have disturbed the cosmic calm, and the star's remains will linger for ages, slowly mixing into the galaxy's interstellar medium. The galaxy itself is now a little richer in heavy elements, thanks to this one star's life and death. In time, those scattered atoms will drift through space and coalesce into new cosmic structures. Out of the ashes of this stellar inferno, new light will one day emerge. Even as we bid farewell to this star, the grand cosmic ballet continues. Every death in the universe paves the way for new birth among the stars. In the silent aftermath of a supernova, a ghostly nebula drifts through the darkness of space. What was once a mighty star has been torn apart, its stellar materials strewn across the cosmos in a glowing cloud. Yet this violent end is not a final death. Within the expanding debris lies the promise of new beginnings. Those clouds of gas and dust are enriched with the star's most precious gifts, elements forged in its heart that will seed the birth of future stars. For years and centuries after the explosion, the nebula continues to expand and evolve. A shockwave from the blast races outward, ploughing into the surrounding interstellar gas. As it travels, it compresses and stirs up that gas, like a cosmic ripple, squeezing clumps of matter together. In these denser pockets, gravity can take hold once again. Slowly, the scattered remains begin to gather, and within the chaos, new stars can quietly kindle. For a moment, one star's death can outshine a whole galaxy, but it is also a spark for new life in the cosmos. The shock of the supernova does more than destroy. It also breathes new energy into its surroundings. Great clouds that were once cold and still are jolted awake by the expanding blast. They fragment and collapse under their own gravity, each fragment destined to ignite as a new star. In this way, one blazing demise leads to a family of newborn stars scattered amid the fading glow of the remnant. For the transformation of chaos into new suns, patience is woven into the cosmos. Nothing happens in a single human lifetime. The process spans tens of thousands to millions of years. Long after the initial flash has faded, the supernova's aftermath continues its work. Over millennia, the expanding shell of gas grows to tens of light years across, sweeping up and mixing with any gas it encounters. Only after eons do dense knots within that shell begin to shine as infant stars, emerging from the residue of the once great star. As these nascent stars take shape, they inherit the matter of their ancestor. The gas that gathers into each new sun is laced with heavy elements forged in the previous star's core. In earlier epochs of the universe, such elements were scarce. New stars born then were almost pure hydrogen and helium. But now, thanks to generations of stellar lives and deaths, the raw material is richer. Each new star is a little different because it contains the recycled ashes of its forebears. For a galaxy, this cycle is essential. Without the shock waves and enriched gases from supernova explosions, star formation would slow and stifle. It is often said that without supernovae, there would be far fewer new stars at all. The turbulent push from these blasts helps to gather drifting gas into dense clumps where gravity can ignite new suns. Thus, even as a star's life ends, it ensures the galaxy's creative cycle carries on. In the night sky, some of these cosmic ruins still glow, bearing witness to this renewal. The delicate Crab Nebula, for instance, is the scattered remnant of a long-ago supernova. Its filaments of neon and gold spread outward, the colourful shrapnel of an exploded star mixing into space. Within that expanding cloud, generations hence, new stars may one day spark to life. Even now, hidden in its heart, there are signs of energy that keep the nebula aglow, hinting at the cycle already in motion. Humans have even witnessed such events with the naked eye throughout history. In the year 1054 AD, astronomers in China and elsewhere recorded a strange new star that lit the day sky for weeks. It was a supernova in our own galaxy. Today, nearly 1,000 years later, the expanding cloud of debris from that blast is visible as the Crab Nebula. What those sky watchers observed was the moment of destruction. What we see now is the aftermath, slowly dispersing and readying the raw material for future suns. The cycle that connects that ancient sighting to the stars of tomorrow underscores how intimately creation and destruction are woven together. In each of these new stars, the legacy of the old lives on. But the story does not end with stars alone. The heavy elements scattered by that supernova, carbon, oxygen, iron, and beyond, do more than just help stars form. They also drift in the surrounding space, ready to become part of something even more complex. Those very atoms will one day collect into solid grains, into rocks and worlds, forging planets from the ashes of the dead star. Around a newborn star, a flattened disk of gas and dust swirls like a cosmic whirlpool. This dust is the pulverized remains of older stars, rich with heavy elements like silicon, iron, and carbon. Over time, the fine grains begin sticking together, forming clumps and pebbles amid the disk. Gently, inexorably, these pieces collide and merge, building up larger and larger bodies. In this quiet accretion, the ashes of long-dead suns are assembled into brand new planets. In our own solar system, this process played out some 4.6 billion years ago. A cloud, enriched by earlier supernovae, collapsed to form the Sun, and a disk of leftover dust circled around it. Within that disk, dust grains, some of them older than the Sun itself, combined to form rocks and planetesimals. Piece by piece, the planets grew. The Earth, along with its sister worlds, slowly emerged from this cosmic debris, built of elements born in stars that died long before our world existed. Clues in ancient meteorites suggest that a star's death may have directly influenced our solar birth. Scientists have found telltale traces of short-lived radioactive elements in meteorite fragments, atoms that could only have been produced in a supernova explosion. These traces hint that, as our Sun's natal cloud was forming, a nearby supernova enriched it with fresh material, and perhaps gave it a nudge. In a way, a dying star might have been the midwife to the Sun and planets, providing both the raw ingredients and the push to bring them together. Every world that solidifies in such a disk carries the fingerprints of stellar alchemy. The iron at Earth's core was forged in the heart of a massive star. The calcium in our bones and the silicon in the sand under our feet were formed in stellar furnaces and scattered by ancient supernova. Our blue planet's very substance, its rocks, its oceans, its atmosphere, is built from elements cooked in multiple stars over billions of years. Without these heavy elements, Earth could never have been the diverse, life-supporting world we know. As we look out into the galaxy, we find that where heavy elements abound, planets follow. Stars born in regions enriched by many past supernovae tend to host rich families of planets. By contrast, stars with too few heavy elements may have scant material to form worlds. This correlation tells a simple story. The more stardust available, the more likely the cosmos is to craft new planets. Over billions of years, as more stars lived and died, the galaxy gradually increased its planetary bounty, setting the stage for countless possible new havens. Around other stars in our galaxy, astronomers have discovered a staggering variety of planets. Gas giants, 10 times the mass of Jupiter, rocky super-Earths, and exotic worlds of all kinds. None of these could exist without the heavy elements made by prior generations of stars. In fact, we observe that stars with higher heavy element content tend to host more planets, indicating that metals are a key ingredient for building worlds. Images of young star systems show disks of dust and gas with gaps carved by forming planets, confirming that planet birth is a common outcome of star formation. Thus, the ashes of old stars give rise not just to solitary worlds, but often to entire planetary systems teeming with diversity. Yet planets alone are not the final chapter of this story. On at least one planet, all those stellar ingredients combined in just the right way to spark something even more remarkable: life. It is on worlds like Earth, built from star-born elements, that chemistry can evolve into biology. The carbon, nitrogen, oxygen, and other elements from ancient supernova explosions became the foundation for living cells. In a very literal sense, the emergence of life is the universe waking up through the materials forged in stars. Life on Earth is deeply connected to the stars. The elements required for biology, carbon, hydrogen, oxygen, nitrogen, phosphorus, and more, were all formed by stars and spread through explosions. In the young universe, before the first stars died, these ingredients were absent. Only after generations of stars lived and exploded could the chemical richness needed for life accumulate. Every atom in a living cell, apart from the most primitive hydrogen, is a legacy of stellar furnaces and supernova fireworks. The connection is intimate. We are, quite literally, made of stardust. The iron flowing in our blood was once inside the core of a star. The calcium in our teeth and bones was forged in stellar heat. The nitrogen in our DNA, the oxygen in the air we breathe. Nearly every element that makes us alive was created by stars and scattered across space by their violent ends. Without those stellar explosions distributing the elements, the complex chemistry that builds life would not exist. Imagine a universe with no supernovae, where stars lived quiet lives and faded without explosion. Such a cosmos would have remained forever primitive, filled mostly with hydrogen and helium gas, lacking the heavy elements that form planets and organisms. No carbon for cells, no oxygen for respiration, no iron for blood. Without the catastrophic deaths of stars to forge and disperse these elements, life as we understand it would simply not be possible. The violence of stellar death was a necessary prelude to the gentle emergence of life. But supernovae have likely influenced life in other ways beyond providing materials. They also bathe the galaxy in cosmic rays, high-energy particles that zip through space and occasionally through living cells. Over Earth's history, these cosmic rays, largely born of stellar explosions, may have subtly affected life's evolution. By slightly increasing mutation rates or altering atmospheric chemistry, they could have nudged biological paths in new directions. In this way, stellar explosions might have even shaped the story of life's development on our planet. There is evidence that at least once in the Earth's past, a supernova occurred close enough to leave its mark. Scientists have discovered traces of exotic isotopes, like iron-60, in ancient seabed layers, atoms that rained down from a supernova explosion a few million years ago. That cosmic event, just a few tens of light years away, might have impacted Earth's climate and biology. Some speculate it contributed to extinctions or evolutionary shifts by flooding our planet with radiation. It is a reminder that while supernovae give life's ingredients, they can also influence life's journey in unpredictable ways. For the most part, however, the Earth has been at a safe distance from the truly dangerous blasts. In the grand balance, the benefits of supernovae far outweigh the risks. They have endowed our world with a diversity of elements and provided the spark of creation while rarely posing harm. In the darkness of space, each supernova is both a destroyer and a creator, an agent of chaos that ultimately enabled something as delicate and ordered as a living cell. It is a profound cosmic irony and wonder that the death of stars underpins the vitality of life. Interestingly, this pattern of creation through destruction is mirrored in other realms of nature. On Earth, a forest fire may seem purely destructive, but it clears dead wood and returns nutrients to the soil, allowing new plants to thrive. Similarly, a star's violent end clears space in its region and enriches the cosmic dust with elements that will feed new stars and planets. It's a cosmic version of ecological renewal, a cycle where an ending is simply the preparation for a new beginning. This creative destruction means that, at every scale, from galaxies to forests, death can sow the seeds of life and renewal. In the aftermath of a supernova, not only are elements scattered across space, but something extraordinary may remain at the explosion's center. When a massive star dies, its core can survive as a dense, exotic object. While the debris of the star goes on to nurture new worlds and life, the collapsed core becomes a strange new kind of star. It no longer shines like the sun, yet it pulses and beams with uncanny regularity. These stellar corpses, pulsars and magnetars, are the next chapter in the story, revealing how bizarre the universe can be, even after a star's life has ended. Imagine a star's core crushed so tightly that atoms themselves collapse. Electrons and protons squeeze together, forming a sphere of nearly pure neutrons. This neutron star is incredibly small, only about 10 or 20 kilometers across, yet contains more mass than our Sun. Its density is inconceivable. A teaspoon of neutron star material would weigh billions of tons. This is the state of matter in a pulsar or magnetar, a city-sized stellar corpse born from the violence of a supernova. On the surface of such a star, gravity is overwhelmingly strong. A person standing there, if one could survive, which they could not, would feel billions of times more gravity than on Earth. Any mountains or bumps are flattened by the intense pull. The crust of a neutron star is smooth and hard, likely made of iron. Time and space themselves are warped by the gravitational field. This tiny remnant is essentially a gigantic atomic nucleus, held together by gravity so fierce that light itself struggles to escape. Neutron stars also spin, sometimes at astonishing speeds. As the original star's core collapsed, it rotated faster, much like a figure skater pulling in their arms. Some pulsars rotate dozens of times each second. A few rotate hundreds of times a second, incredibly. This rapid spin, combined with a strong magnetic field, drives twin beams of radiation from the star's magnetic poles. These beams sweep around as the star spins, creating a lighthouse effect. When one of those beams crosses Earth's line of sight, we detect a pulse of radio waves or light, giving the pulsar its name. When pulsars were first discovered in the late 1960s, their signals were so regular that astronomers were mystified. The radio pulses arrived like clockwork, precise to the millisecond. The discoverers half-jokingly labelled the first source LGM-1, which stood for Little Green Men, wondering if it could be an alien beacon. It was soon understood that this was no artificial signal, but a rapidly spinning neutron star. The pulse's steady beat was nature's own cosmic clock, ticking with astonishing precision. Indeed, pulsars are some of the most reliable timekeepers in the universe. Certain millisecond pulsars are so regular that their spin period only drifts by perhaps a few billionths of a second over years. Astronomers use them as celestial clocks, and even to detect gravitational waves subtly stretching and squeezing space. Future navigators might one day use pulsars like a galactic GPS, mapping their positions and pulse timings to find their way through space. It's remarkable to think that a dead star's heartbeat could guide spacecraft with pinpoint accuracy. Incredibly, even planets can exist around these stellar remnants. In fact, the first exoplanets ever confirmed in the early 1990s were found orbiting a pulsar. Astronomers were astonished to discover tiny worlds circling a neutron star, likely formed from the debris of the star's explosion. Imagine a planet bathed not in the gentle light of a sun, but in the fierce pulses of a pulsar, an eerie environment, yet one that proves the resilience of planetary formation. Even in the aftermath of destruction, the cosmos finds a way to rebuild, assembling new worlds in the unlikeliest of places. Not all neutron stars are gentle, steady beacons. Some are far more volatile. These are the magnetars. A magnetar is a neutron star with an unimaginably strong magnetic field, hundreds of trillions of times stronger than Earth's field. This magnetic power can twist and stress the star's crust until it cracks in a starquake. When that happens, the magnetar can erupt with a burst of high-energy radiation. Magnetars are like the ticking time bombs of the stellar graveyard, usually quiet but prone to sudden, violent tantrums. In December of 2004, astronomers witnessed just how powerful a magnetar's fury can be. A magnetar on the far side of our galaxy, about 50,000 light-years away, underwent a colossal starquake and flare. In a fraction of a second, it released as much energy as the sun emits in 100,000 years. The burst of gamma rays was so intense that it lit up detectors on spacecraft and briefly ionized Earth's upper atmosphere, even from that immense distance. Had such an eruption happened within a few light-years of us, it could have been catastrophic. Fortunately, the nearest magnetars are thousands of light-years away, and we observed this outburst safely from afar, awed by the spectacle. These magnetar flares may also help explain other cosmic mysteries. In recent years, astronomers have detected sudden, millisecond-long flashes of radio energy called fast radio bursts, whose origins were unknown. One theory gained traction when a magnetar in our own galaxy was caught producing a weaker radio burst at the same time as an X-ray flare. It suggested that at least some fast radio bursts could be magnetars unleashing their energy. Even after death, these stars continue to surprise us with new phenomena, challenging our understanding of physics under extreme conditions. For a moment, consider the strangeness of a pulsar or magnetar from a human perspective. A once glorious sun has become a dense ember, spinning madly and crackling with magnetic fury. It can hardly be seen except through its rhythmic signals or sudden outbursts. If a habitable world somehow orbited such a thing, its sky would be dominated by an object no larger than a city that outshines everything whenever its beam sweeps past. This scenario might seem like science fiction, yet the universe hosts these exotic remnants throughout galaxies, each one a reminder of a star that was, and an enigmatic afterlife that is. As extreme as pulsars and magnetars are, there are cosmic explosions even more powerful than a typical supernova. Some dying stars produce blasts so intense they release more energy in seconds than the sun will in its entire lifetime. These are the gamma ray bursts, brief flashes of gamma radiation that can outshine entire galaxies. They are the most violent explosions known in the universe. Pulsars and magnetars show us the strange behavior of stellar corpses, but gamma ray bursts mark the final scream of certain stars or collisions, a level of destruction and energy almost beyond comprehension. In a far-off galaxy, a massive star's core implodes in the ultimate catastrophic collapse. Almost instantly, the infalling star forms a newborn black hole at its center. From the black hole's poles, two intense jets of energy punch through the collapsing star and blast into space at near the speed of light. For a brief moment, the dying star emits a flood of gamma radiation, so brilliant it outshines 1,000,000 galaxies. This is a gamma ray burst, nature's most powerful flash, a cosmic beacon visible across the universe. Gamma ray bursts, GRBS, come in two main varieties, both terrifying in scale. Some, like the one just described, are long-duration GRBs, lasting several seconds to minutes. They originate from the collapse of extremely massive stars, sometimes called a hypernova. In other cases, GRBs are very short, lasting less than 2 seconds. These short bursts are thought to arise not from single stars collapsing, but from catastrophic collisions. For example, 2 neutron stars spiraling into each other, or a neutron star merging with a black hole. Despite the difference in origin, both types unleash mind-boggling energy. Gamma-ray bursts were first discovered by satellites in the 1960s, catching scientists by surprise. Originally detected by military satellites searching for nuclear bomb tests, these flashes of gamma rays were coming from deep space. For decades, GRBs remained mysterious. Brief, random blips of intense radiation with no obvious source. It wasn't until the late 1990s that astronomers managed to pinpoint their locations and identify afterglows in X-ray, optical, and radio wavelengths. We learned that gamma-ray bursts were occurring in distant galaxies, billions of light-years away, their incredible brightness allowing us to see them across the cosmos. For those few seconds of a GRB, the amount of energy being hurled out is almost unthinkable. A single gamma-ray burst can emit as much energy as our Sun will produce over its 10 billion year lifetime, all in the blink of an eye. In fact, if a GRB happens in a distant galaxy, it can briefly appear as bright as all the stars in that galaxy combined. Some GRBs have been so luminous that astronomers have detected them with the naked eye from Earth, despite being billions of light years away. An example occurred in 2008. It's as if a cosmic camera flash went off in the distant darkness. What makes GRBS so extraordinarily powerful? In the case of a long GRB, when a massive star collapses, the core forms a black hole and the infalling material gets blasted outward along rotation axes as jets. These jets are extremely focused, so the energy, instead of radiating in all directions, is concentrated into narrow beams. If one of those beams is aimed toward us, we see a gamma-ray burst. The short GRBs, on the other hand, result from merging dense objects. Their collision releases a surge of energy and also focuses some of it into jets. In both scenarios, the physics at play involve ultra-strong magnetic fields, shock waves, and particles accelerated to nearly light speed, all creating an intense burst of gamma rays. After the initial flash of gamma rays, a GRB often leaves behind an afterglow that can linger for days or weeks. As the jets slam into surrounding interstellar gas, they produce bright emissions in X-ray, optical, and radio that gradually fade. In the case of neutron star mergers, which cause short GRBs, another phenomenon occurs: a faint optical display called a kilonova. This kilonova is the glow of freshly forged heavy elements, like gold and platinum, created in the merger and ejected into space. Such events are not only powerful explosions, but also cosmic forges, manufacturing some of the rarest elements in the universe. One recent cosmic event allowed us to witness these processes in unprecedented detail. In 2017, scientists observed 2 neutron stars merge in a galaxy 130 million light-years away. An event detected both via gravitational waves and a short gamma-ray burst. As the neutron stars collided, observatories recorded ripples in space-time and a brilliant glow of a kilonova rich in heavy elements. It was a spectacular confirmation that such mergers produce short GRBs and forge elements like gold. This multi-messenger observation, using both gravity signals and light, opened a new window on how violent cosmic events sculpt the universe. Given their power, one might wonder what would happen if a gamma-ray burst occurred near our planet. Astronomers believe that a GRB within a few thousand light-years could have serious effects on Earth's atmosphere and life, The intense gamma radiation could strip away the ozone layer, allowing harmful ultraviolet sunlight to reach the surface, potentially triggering mass extinctions. Some researchers hypothesize that a gamma-ray burst might have been responsible for at least one extinction event in Earth's distant past. Thankfully, such nearby GRBS are extremely rare. The known bursts we observe are at cosmological distances, posing no immediate threat to us, but serving as cautionary tales of nature's extremes. Besides their dramatic nature, gamma-ray bursts are useful to scientists as probes of the distant universe. Because they are so bright, we can detect GRBs from very early epochs of cosmic history, billions of years in the past. The light from a gamma-ray burst can carry information about the gas and dust it passes through on its way to Earth, allowing astronomers to study the properties of distant galaxies. In a sense, GRBS act like flashbulbs that briefly illuminate the far reaches of the cosmos, revealing glimpses of the universe's youthful eras not otherwise easily seen. Each detection of a GRB not only tells us about an extraordinary explosion, but also about the environment it exploded in, adding pieces to the puzzle of cosmic evolution. In witnessing gamma-ray bursts, we observe the cosmos at its most violent. Yet even these cataclysms tie back into the grand cycle of creation and enrichment. The heavy elements forged in these explosions, whether in hypernovae or neutron star mergers, spill out into space, joining the galactic medium. In time, that material will be incorporated into new stars and planets. So the most powerful blasts, like all aspects of massive star death, feed into the cosmic web of gas and dust, contributing to the ongoing evolution of galaxies. We step back now from individual explosions to see the bigger picture, how each death, each burst of energy, connects into the vast tapestry of the universe. Step by step, death by death, massive stars have transformed the universe from its pristine beginnings to the rich tapestry we see today. In the first few 100 million years after the Big Bang, the cosmos was devoid of the heavier elements. No carbon, no iron, no oxygen. The earliest stars, huge and short-lived, were the pioneers. They forged the first heavy elements and dispersed them in primal supernovae. Those materials seeded early galaxies with the ingredients for the next generation of stars. With each subsequent stellar death, more elements spread outward, gradually enriching the cosmic environment. Galaxies are ecosystems of stars, gas, and dust, and supernovae are a key regulator in their life cycles. The heavy elements and energy released by stellar explosions influence how and where new stars form. Early galaxies, lacking metals, formed stars differently than modern galaxies do. Over billions of years, as supernovae and mergers infused galaxies with metals, the behavior of gas changed, cooling faster, fragmenting into smaller clumps, birthing stars more efficiently. The result is that stars today, like our Sun, contain far more heavy elements than those first stars. The chemical evolution of a galaxy is essentially the story of countless star deaths, enriching it over time. The influence of stellar death is not confined within galaxies. Powerful supernova-driven winds can blow gas out of a galaxy's confines, especially in periods of furious star formation. In starburst galaxies, or during galaxy collisions, myriad supernovae act together to create galactic winds that carry gas laden with metals into intergalactic space. Over cosmic time, this process has seeded the diffuse gas between galaxies, the cosmic web itself, with heavy elements. Thus, even the tenuous filaments of gas stretching between galaxy clusters are enriched by the ashes of stars. The cosmic web, an immense network of matter, has been gradually metal-enriched by generations of exploding stars. Astronomers today find evidence of this vast enrichment. When we analyze the light from distant quasars, we see signatures of heavy elements in the intervening gas clouds, proving that even the far reaches of intergalactic space are not pure hydrogen. Those atoms, oxygen, carbon, iron, floating in the void, are fossils of ancient star explosions, blown out of galaxies eons ago. The universe has recycled and shared its materials broadly. What was once inside a star now drifts in the space between galaxies, ready to be incorporated into the next generation of stars and planets, wherever gravity draws the gas together again. In this way, the entire cosmos is interconnected by the dispersal and mixing of elements, forming a kind of chemical web linking countless star systems. This cosmic web of enrichment has personal significance too. Every atom in our bodies has journeyed through this cycle. The gold in a wedding ring might have been forged in a neutron star collision billions of years ago, then cast across space and eventually embedded in the Earth. The oxygen we breathe likely came from multiple supernovae that enriched the cloud which formed our sun. We, as living beings, are direct beneficiaries of countless stellar deaths. In a very real sense, our existence is a meeting point of matter from all over the galaxy, a chemical convergence orchestrated by the life and death of stars. As we gaze up at the night sky, we can appreciate that the twinkling stars and faint nebulae are all part of this ongoing cosmic cycle. Every glimmering point is either in the process of creating elements or will one day release them back into space. The Milky Way itself is a vast, dynamic web of stellar alchemy and recycling, where destruction and creation continuously intertwine. The legacies of massive stars' destruction live on in us, in the planets, and in the glow of future stars not yet born. The universe, through these processes, continually renews itself, an endless story of endings becoming new beginnings. Looking far ahead, we can imagine a time in the distant future when star formation has slowed as the raw fuel is used up. Fewer new stars will light up, but the galaxy will still contain all the heavy elements and structures built during its vibrant youth. Even as the era of starbirth winds down, the legacy of those millions of supernovae and kilonovae will remain in the enriched matter spread everywhere. Perhaps in that far future, that material will be part of new and different cosmic structures, or even reused by forms of life or intelligence we cannot yet fathom. For now, we live in a cosmic age rich with heavy elements and ongoing star formation, a time when the cycle of stellar life and death is in full bloom, connecting us intimately to the past and shaping the future. Even now, our exploration is not finished. The more we learn about the lives and deaths of stars, the more deeply we understand our own origins and the workings of the cosmos. And still, mysteries remain, enigmas of extreme physics and cosmic fate that await discovery. Each chapter we uncover in the story of massive stars only leads to further questions and wonders. The cosmic saga continues as we carry on our journey through the universe's grand tapestry, ever curious about what will unfold next. On a still, dark night, when we tilt our heads upward, we are greeted by countless stars scattered across the sky. The creamy band of the Milky Way arches overhead, composed of myriad stars, too faint to see individually, yet collectively lighting the sky. Among the glittering points shine the rare, massive beacons that have fascinated humanity for generations. The red-orange glimmer of Betelgeuse marks Orion's shoulder, while the icy blue of Rigel adorns his foot. These stars captivate us with their beauty and brightness. They flicker ever so slightly as the atmosphere dances, each twinkle a gentle reminder of the vast gulf between us and those distant fires. Yet there is a subtle melancholy in their splendor, for we know that such stars live fast and die young. The very brilliance that makes them stand out is a herald of their impermanence. As we gaze at Betelgeuse, twinkling with its reddish hue, we might reflect on its fate. It is a colossal star nearing the end of its life. Someday, perhaps tomorrow, perhaps 100,000 years from now, Betelgeuse will explode as a supernova, blazing brighter than the full moon in Earth's sky. Many of us today watch Betelgeuse closely, wondering if we might be the lucky generation to witness its final blaze. The thought stirs excitement and a hint of sadness. We would be seeing a marvel, but also saying goodbye to a familiar friend in the sky. For weeks, maybe months, the supernova will cast shadows at night and even be visible in daylight, an almost unimaginable spectacle. And then, just as suddenly, it will fade away, leaving Orion without his bright shoulder. To future sky watchers, the familiar pattern of Orion will look different, missing that vibrant star. What was once a constant point of light for us will become, in cosmic terms, a memory, a faint haze of expanding gas visible only through telescopes. Many of the stars that draw our eyes are likewise short-lived. The sparkling blue-white jewels of Orion's belt, for instance, are hot, massive stars, only a few million years old. In a few million more years, they will burn out and vanish, long before the slower-burning, dimmer stars around them survive. The grand constellation figures celebrated in our myths are transient arrangements. If we could watch the sky's patterns over eons, we would see them change shape and character. Constellations would lose bright stars and gain new ones as massive stars die and others are born. The very sky lore we pass down, hunters, heroes, and animals traced in starlight, is a shifting story written across deep time. When we consider the light of a distant star, we are also looking back in time. The beams that reach our eyes left their source years, centuries, or millennia ago. For some of those massive stars, it's possible that by the time their light arrives here, the star itself has already perished. We could be admiring the glow of a star that no longer exists, a ghost light travelling alone through space. There is something profoundly poignant about that idea. It is a solemn reminder of the vast timescales at play. A star's death announcement, travelling eons before reaching our eyes. The night sky becomes not just a view of space, but a kind of time machine showing us many stars, not as they are now, but as they were long ago. It reminds us that all things, even brilliant stars, have their moment and then pass on. Yet, knowing this impermanence makes the act of stargazing even more special. When a bright star, like Deneb in Cygnus or Antares in Scorpius, catches our attention, we pause to appreciate that we are witnessing a fleeting chapter of a cosmic tale. Antares, with its deep red sparkle, is another supergiant nearing the twilight of its life. One night, it too will wink out in a tremendous explosion. But tonight, it shines for us, steady and ancient seeming, its eventual fate hidden behind a veil of time. We feel fortunate to behold it in the brief window during which its light graces our skies. Every few decades or centuries, humanity is treated to the appearance of a new star in the firmament, the sudden flare of a supernova in our galactic neighborhood. In 1987, for instance, a supernova exploded in a neighboring galaxy and became visible to the naked eye, offering modern astronomers their first chance in centuries to study a nearby stellar death in real time. To those who see such an event, it can be a disorienting, almost mystical sight. A star, where none was before, outshining even planets, then disappearing after a short while. Ancient peoples recorded such sights with awe and sometimes fear. Ancient sky watchers often regarded these phenomena as omens or divine events, a mix of fear and wonder that shows how powerful the impact of a supernova's appearance can be on the human psyche. In our modern era, we understand what we are seeing and can marvel in a different way, with both wonder and knowledge. We recognize it as a massive star's farewell, and we also see the promise it carries, the dispersal of new elements, the seeding of future worlds. Under the quiet canopy of the night, one cannot help but feel a mix of emotions when contemplating the massive stars above. There is wonder, for their light has travelled immense distances to reach us, and their power is beyond comprehension. There is humility, for we perceive how small and short-lived we are next to the cosmic fires that can burn for millions of years. And there is a gentle sadness in knowing that nothing in the universe, not even the stars, lasts forever in their prime. But that sadness is tempered by an appreciation of the cosmic cycle. We understand that when a bright star disappears, it is not truly gone, but transformed, and its light and material will reappear in new forms elsewhere. For a lone observer on a hilltop far from city lights, time seems to stand still under that shimmer of stars, as if the universe is telling its story in hushed, twinkling voices. So we stand under the stars, perhaps on a cool night with crickets singing in the distance, and we allow ourselves to simply be present in their glow. The massive stars that have ignited the heavens with their brilliance invite us to ponder time and change. They encourage us to cherish the moments of beauty that flicker briefly in our lives and in the cosmos. In the end, the fleeting existence of these stellar giants makes them more precious, not less. Their brief light enriches the sky, just as their violent deaths enrich the galaxy. As we watch them, we find ourselves filled with wonder, not only at what we see, but at the knowledge that we are witnessing a grand cosmic story unfolding silently above us. Which of these stars will be the next to bid farewell in a cosmic firework? Will it happen in our lifetime, allowing us a front row seat to one of nature's grandest finales? Moments ago, a brilliant flash of a supernova lit up the darkness, marking the death of a star. In the quiet afterglow of catastrophe, the cosmos holds its breath. The explosion has passed, and silence returns to the cosmic night. In the void, where a mighty star once shone, a delicate cloud of gas and dust now drifts through space. This glowing nebula is the scattered ash of a star's violent death, spreading slowly across light years of vacuum. Faint tendrils of the nebula glow with a reddish hue, lit by the fading energy of radioactive elements created in the blast. At first glance, it seems like an ending, a silent graveyard of what once was. Yet within these ghostly filaments lies the promise of a new beginning. Over time, gravity begins to weave its subtle spell on the debris. Wisps of gas draw closer together, gently gathering into denser clumps. The cloud, once diffuse and shapeless, starts to develop bright knots and dark, coiling lanes. Deep in the heart of one such knot, matter starts to pool, ever so slowly, yet inexorably. If one could drift within that cloud, there would be darkness all around, punctuated by faint glimmers where new stars struggle to be born. The airless silence would be broken only by the gentle pressure of particles and the distant radiance of neighbouring stars hinting through the haze. Thousands upon thousands of years slip by in this quiet assembly, as the cloud's densest pockets grow heavier and warmer. In one hidden core, shielded by curtains of dust, the temperature inches upward with every passing millennium. Eventually, the pressure and heat at the center of this collapsing cloud reach a critical point. In that moment, like a spark catching flame, nuclear fusion ignites. A newborn star flickers to life, its infant light pushing back the darkness of its natal cocoon. What was once cold dust and atomic ash is now a sphere of radiant fire. From the tranquil darkness emerges a new star, breathing light and warmth into the space around it. Its first rays pierce the gloom, illuminating the nebula from within. A gentle wind of radiation and particles flows out from the young star, slowly clearing away the veils of dust. Bit by bit, the newborn sun unveils itself to the cosmos, a tiny beacon growing steadily in brilliance. In stellar nurseries across the cosmos, this drama unfolds again and again. In the constellation of Orion, a great nebula glows softly, where hundreds of young stars are being born from clouds of gas. Bright blue-white beacons illuminate swirls of crimson and violet nebula, painting the night with ethereal light. In the Eagle Nebula, the famous pillars of creation are just such nurseries, towering columns of gas and dust being sculpted and illuminated by newborn stars hidden within. Amid pillars of dust sculpted by starlight, new suns take shape. From what appears as mere wisps through a telescope, entire clusters of stars can emerge, each a beacon ignited from darkness. Often, dozens or hundreds of newborn suns form together in these nurseries, a loose family of stellar siblings born side by side. They begin life close to one another, their youthful lights mingling in the cloud. In time, as they orbit the galaxy, this star family may drift apart, scattering its members across the cosmos, but the shared origin forever links them. This is the cosmic circle of life, from dust to fire and back to dust. The young star will burn brightly, fueled by the remnants of its ancestors' scattered elements. In its core, the legacy of the previous star lives on as new elements fuse and fresh energy radiates outward, surrounding this stellar cradle. Leftover gas and dust swirl in a luminous haze, some coalescing into planets or moons, some drifting as fine stardust, waiting for another chance to fall into a future sun. As the star grows and stabilizes, it shines steadily for eons, illuminating the nebula that once cocooned it. It may live for millions or even tens of millions of years, but compared to the timeless galaxy, its lifespan is only a brief chapter. In time, it too will exhaust its fuel. When that day finally comes, the star's brilliance will falter. It might swell into a bloated giant or tremble with instability in its final epochs. And at last, perhaps in another mighty supernova or a gentle shedding of outer layers, it will cast its essence back into space. And so the cycle continues, one generation of stars giving way to the next. The debris from one star's death becomes the raw material for new stars and new worlds. Each time the cycle repeats, more complex atoms are mixed into the cosmic brew. The calcium in rocky worlds, the oxygen in distant skies, the iron in planetary cores. Each ingredient was forged in some ancient stellar furnace. Scattered by explosions, these atoms drift for ages until gravity draws them into new suns and planets, enriching the universe bit by bit. In this repeating pattern, there is a profound harmony and continuity. A star is born out of the gentle gathering of what a predecessor left behind. It lives its life in graceful brilliance, then ends in a final blaze that sows the seeds of future stars. Seen from afar, a glittering nebula with a newborn star nestled within it tells a timeless tale. It is the story of an eternal rebirth written across the stars, a calm assurance that even in destruction there is the promise of new light, like a cosmic phoenix rising again and again from its own ashes. Each star's death brings forth new life among the heavens. In a sense, this cycle of stellar death and rebirth is the heartbeat of our galaxy. It ensures that generation after generation, the lights of creation never go out. Each end heralds a new beginning, and so the cosmic fires keep burning, carrying the story of the universe forward. The night sky we see is made richer and more vibrant by this constant renewal, as if the galaxy itself is continually rejuvenated by its stars. Not all stars live quiet lives or die ordinary deaths. Among the cosmic population are a few stellar titans that push the very limits of size and brightness. These are the rare behemoths of the galaxy, stars so massive and intense that they defy the norm. In hushed corners of space, one might find a star shedding its own skin, casting off shells of gas and exposing a brilliant hot heart within. This is a Wolf-Rayet star, an ultramassive sun stripped down to its burning core. Wolf-Rayet stars are among the hottest and most luminous stars known. Their exposed surfaces sear at tens of thousands of degrees, far hotter than the surface of our sun. In their brilliance, they shine tens of thousands, even millions of times brighter than the sun, flooding their surroundings with fierce ultraviolet light. But this brilliance comes at a cost. The star's radiation is so intense that it drives a powerful stellar wind, a continuous gale of particles that blows the star's outer layers into space. Over mere hundreds of thousands of years, a Wolf-Rayet star can shed material equivalent to the mass of our sun or more, a staggering loss that would take ordinary stars billions of years. As the Wolf-Rayet star casts off its outer layers, it often surrounds itself with a glowing nebula made of its own shed material. Through telescopes, some of these stars are seen wrapped in expanding shells or rings of gas, like cosmic halos, marking the star's life stages. Each shell is a chapter of the star's story, cast off with each new burst of wind. In some cases, these concentric shells appear almost like the growth rings of a tree, each one a fleeting record of the star's past. In one spectacular case, a Wolf-Rayet star orbiting a companion has cast off shells of dust at regular intervals, forming concentric rings, expanding into space like the ripples on a cosmic pond. The remarkable regularity of the shells lets us almost count the star's final beats. One notable pair of stars has formed at least 17 such dust shells over centuries, each shell marking the time of a close orbital embrace. These expanding rings, gently pushed outward by starlight, are a visual timeline of the star's last millennia. Because Wolf-Rayet stars are so intense, they do not last very long, burning up their fuel and blasting their bulk out into the cosmos on a very short timescale, only a few 100,000 years. Such a brief flicker in time means it is unusual to find more than a few of these stars in an entire galaxy. Such stars are extremely rare. In a galaxy of hundreds of billions of stars, only a few hundred at most are Wolf-Rayet stars. To put their rarity in perspective, out of the hundreds of billions of stars in the Milky Way, only a few hundred are in the Wolf-Rayet stage at any given time. A proportion so small, it's as if you searched a whole city to find just one glowing ember. They are the surviving core remnants of once larger stars that have burned so hot and fast that they've peeled away their own outer layers. To find one is to catch a star in its final act before a dramatic finale. Indeed, a Wolf-Rayet star is often a precursor to an explosive end. Having revealed its inner furnace and run low on fuel, it stands on the threshold of a supernova. At any moment in cosmic terms, it may collapse under its own gravity and erupt in one of the most powerful explosions in the universe. Even among these giants, there are those that are stranger and more extreme. Consider the stars that swell to incomprehensible size, red supergiants and hypergiants. These are massive stars that in their old age have bloated into enormous, cooler stars with ruddy hues. Their surfaces cool to a dull red glow, but their size is astonishing. A star like this can grow so large that, if placed at the center of our solar system, it might extend beyond the orbit of Mars or even Jupiter. Imagine a star that would fill the sky from one horizon to the other, its enormous globe dwarfing the entire orbits of planets. In fact, one of the largest known, a red hypergiant called UY Scuti, could extend near to Saturn's orbit if placed at the Sun's position, a nearly incomprehensible span. Light itself would need hours to cross such a star's colossal diameter. These extreme giants are comparatively cooler and gentler in appearance than the searing Wolf-Rayets, but they are no less remarkable in scale. One such crimson behemoth, known as VY Canis Majoris, has a diameter so large that it could swallow the Earth's orbit many times over. One of its brethren, Antares, the red heart of the constellation Scorpius, shines in our night sky as a bright ruby point, quietly burning through the last of its fuel. Antares is a red supergiant, destined to perish in a spectacular supernova in the future, though in the peaceful stillness of a summer night, it appears unchanging and eternal. Meanwhile, in far-off clusters, blue hypergiants and other exotic stars push luminosity to the brink. Some of the most massive stars ever observed reside in a dense star cluster in a neighboring galaxy, weighing in at over 100 times the Sun's mass. Astronomers have even identified stars at the upper limits of mass that nature allows. In a vibrant star cluster in the Tarantula Nebula, for instance, lies a star estimated to be over 200 times the mass of our Sun. Its brilliance defies description, outshining our Sun by tens of millions of times. Yet such a monster is inherently unstable, barely held together by its own gravity against the fierce pressure of its light. It will race through its life in just a few million years or less, destined to collapse in a titanic supernova, likely leaving behind a massive black hole. Stars like this are exceedingly rare, but they show just how far the extremes of stellar creation can reach. Then there are stars that are not only massive, but violently unstable. Luminous blue variables are one example. Titans that can suddenly brighten or fade as they eject huge amounts of mass in unpredictable eruptions. Like a stellar volcano, such a star can lie quiet for centuries and then suddenly erupt, altering its brightness by a huge factor. Eta Carinae, a star system deep in the southern sky, is a famous case. In the 1840s, Eta Carinae underwent a great eruption, flaring up until it became the second brightest star visible in Earth's sky, outshone only by Sirius for a brief time. It expelled gigantic lobes of gas and dust, so much that it wrapped itself in a cocoon of its own making and dimmed from view. To this day, a beautiful cloud called the Homunculus Nebula surrounds Eta Carinae, lit by the star's light from within, a lasting monument to its outburst. Through modern telescopes, we can see the twin lobes of the nebula it expelled, symmetrically billowing outwards like ghostly balloons of gas, testimony to that great outburst. Such dramatic episodes show how turbulent the lives of extreme stars can be. One moment shining intensely, the next casting off material in a great convulsion. All of these rare giants, Wolf-Rayet stars, red hypergiants, luminous blue variables, represent the most exceptional and short-lived members of the stellar family. They live only a blink of time by cosmic standards. While an average star like our Sun will shine for roughly 10 billion years, a supergiant may last only millions, and a Wolf-Rayet in its final phase perhaps only a few 100,000 years. These stars are like brilliant fireworks, expending their energy in one grand display and then fading. For those brief instants in cosmic time, they dominate their regions of space, sculpting their surroundings with intense radiation and powerful winds. Yet despite their power, their lives are ephemeral. In the end, nearly all of these massive behemoths will meet violent fates. A Wolf-Rayet star, after shedding so much of itself, will likely explode as a supernova, or even a rarer hypernova, possibly forming a black hole in its aftermath. Some might even produce a gamma-ray burst in their dying moments, a flash of high-energy light so potent that for a few heartbeats it can outshine entire galaxies. The red supergiants, like Antares, will collapse and explode, briefly outshining millions of lesser suns before fading into a glowing cloud of remnants. The luminous blue variables may rip themselves apart or settle briefly into Wolf-Rayet-like phases before their ultimate end. For now, while they still exist, these rare colossal stars serve as cosmic laboratories and lighthouses. They create in their cores the heavy elements that will be spread throughout space when they die. They stir the interstellar gas with their mighty outflows, triggering new clouds to condense here and there. To observers, they are points of wonder, impossibly bright, often distant and veiled by dust, yet fundamentally altering their cosmic neighborhoods. In their brief lives, these stellar titans leave an outsized legacy. When one looks up at the night sky and finds the faint glimmer of a Wolf-Rayet star or the distinctive hue of a red supergiant, one is witnessing a rare chapter in the grand story of stars, a chapter that, like all others, will one day close, making way for new chapters to begin. These cosmic behemoths illustrate nature at its most extreme. To catch sight of one, even from afar, is to witness a rare and transient marvel. The universe saves its most flamboyant performances for these giant stars, but they perform on borrowed time. Their legacy, however, endures in the nebula they leave behind, and in the heavy elements they scatter, enriching the cosmic stage for generations of stars to come. Many stars do not live alone. Instead, they come in pairs or even triplets, locked in a gravitational dance around each other. Massive stars in particular often have companions, two brilliant suns orbiting a common center. In the vast darkness, one can imagine these stellar partners circling each other like ballroom dancers under the cosmic spotlight. But this dance can turn deadly as the stars age and change. The fates of binary stars are intertwined, and sometimes they face dramatic and violent ends together. In a close binary system, the two stars may orbit so near that they begin to interact physically. As one star expands in old age, it can overflow its outer layers toward its companion. A famous example of such mass exchange is the star Algol in Perseus. The larger star has shed much of its mass to its companion, creating an unusual situation that once baffled astronomers. Gas streams from one star to the other, forming a bridge of glowing material between them. The larger star, bloated and cooling, finds its mass siphoned away by the smaller but hotter companion. This transfer can strip the massive star of its outer envelope, exposing its hot core, while the smaller star swells with new fuel, growing brighter and hotter. For a time, the binary system can become a strange, conjoined entity, each star influencing the life of the other in profound ways. Sometimes the interaction is more catastrophic. If the stars spiral too close, they can merge into one. Two suns becoming one sounds peaceful, but the reality is explosive. When a stellar merger occurs, an enormous amount of energy is suddenly released. In one case, not long ago, a seemingly unremarkable star system in our galaxy burst forth in a red glow visible to telescopes, then slowly dimmed over months, just the sort of signature left by two stars merging into one. Astronomers have witnessed such events as luminous red novae, a kind of stellar explosion less energetic than a supernova, but still incredibly bright. In these events, a new star flares into view where none was seen before, glowing with a ruby-red light that gradually fades over time. What we are seeing is the aftermath of two stars colliding and coalescing. The merged star may be larger and more stable, or it may be left pulsating and unstable from the upheaval. In either case, a cosmic union of two stars leaves a telltale scar in the sky, expanding clouds of gas, and a remnant star born from violence. Binary fate can also lead to sequences of stellar deaths. Imagine two massive stars orbiting each other over millions of years. The more massive of the pair reaches the end of its life first. It explodes as a supernova, briefly outshining the entire galaxy. For its companion, this is a moment of peril. The blast may rip away the companion's outer layers or kick the companion like a slingshot, sending it hurtling through space as a runaway star. Indeed, astronomers have found such runaway stars speeding alone through the galaxy, likely survivors of these cosmic slingshots. Even the neutron star, or black hole left behind, can recoil from the explosion, careening silently through the void. If the binary remains bound even after the explosion, the system is radically changed. One star has now become a neutron star, or a black hole, while the other is still a living star, orbiting this dark, dense remnant. In such a surviving binary, the dense corpse of the first star can begin interacting with the still living companion. A neutron star, no larger than a city but immensely heavy, might pull gas from the outer layers of its companion. Gas pulled off the living star spirals into a disk around the neutron star, heating to millions of degrees and emitting powerful X-rays. The system becomes an X-ray binary, a beacon of high-energy light flickering in the darkness. All the while, the neutron star and the remaining star continue their orbital dance, one shining, one dark and deadly. Eventually, the second star will also reach the end of its life. It too may explode in a supernova. For a time, there could be two neutron stars locked in orbit, a binary made of two stellar remnants where once two bright stars lived. Over time, even these remnants spiral closer due to the gradual release of gravitational waves, ripples in space-time itself. The dance that began eons ago will reach its finale when the two neutron stars finally collide. In that final moment, they merge with a flash of unbelievable power. The collision of two neutron stars releases a burst of light and energy called a kilonova, a glow that can forge some of the heaviest elements in the universe. Gold, platinum, and other precious elements are created in those brief, furious moments of merging. In recent years, humanity has even managed to catch one of these final dances in action. Delicate detectors on Earth felt the subtle shudder of spacetime as two neutron stars far away spiraled together. It is as if the fabric of space itself shuddered from the impact, sending out silent waves that travel across the universe. Moments later, telescopes detected a new pinpoint of light in the sky, a fading ember from the collision where those stars merged. It was the first time we both heard and saw the same cosmic event, a breathtaking confirmation that even in death, binary stars can create anew, scattering freshly forged elements into the galaxy. Colliding stars do not always end in such exotic remnants. Sometimes two normal stars simply crash together in crowded environments, like the cores of star clusters. In those dense stellar hives, the space between suns is comparatively small, and close encounters are inevitable. The cores of globular clusters, for example, are crowded neighborhoods where stars circle each other like wary dancers, and occasionally even collide head-on. Occasionally, one star may drift too near another and be pulled in, leading to a direct collision. The two stars crash together in a brilliant flash, then merge and settle into a single, rejuvenated star. The result can be an unexpectedly young-looking star in an old cluster, a star that stands out as unusually hot and blue among its aging neighbors, an indication that it was reborn through a merger, given a new lease on life. Astronomers have a name for these rejuvenated stars in old clusters: blue stragglers, stars that appear younger and bluer than their peers, likely because they merged and gained a new life. Whether through direct contact or through the long gravitational waltz to a final collision, binary stars showcase some of the most dramatic processes in the universe. Each binary star system writes its own ending to the tale, some serene and others spectacularly violent. In their interactions, we see that even in the vast solitude of space, relationships can profoundly change the destiny of stars. The quiet dance of two suns can unleash forces that reshape their surroundings and create phenomena visible across millions of light years. It is a powerful reminder that the cosmos is full of interactions, and even the mightiest stars are not isolated in their fate. In the stillness of space, two stars can quietly circle one another for ages. But when their fate catches up with them, that quiet dance can end in a fury, an explosion, a merger, a burst of gravitational energy echoing across the cosmos. It is a dramatic crescendo to a duet that may have lasted millions of years, and it reminds us that even in the vast emptiness, chance meetings and close relationships can spark the brightest of fires. Across the sweep of cosmic time, massive stars have been key actors in the grand story of the universe. In the beginning, there was darkness and a faint afterglow, the dwindling light of the Big Bang fading into a cosmic night. The universe then was a fog of hydrogen and helium gas, pristine and untouched by any star. But gravity worked patiently, drawing clouds of gas together, and at some point, the very first stars ignited. One might envision that moment as the universe's first dawn. After ages of darkness, a brilliant star flickered to life, casting the first true shadows in the void and illuminating its surroundings. These first stars were unlike those we see today. Astronomers refer to these hypothetical pioneer stars as population 3 stars. Born in a universe with no heavy elements, they may have grown to extraordinary mass, hundreds of times the mass of our Sun, because nothing was there to easily cool the gas and break it into smaller pieces. Without carbon, oxygen, or dust to radiate away heat, the gas clouds formed only a few giant stars, rather than many smaller ones. These behemoths took shape virtually unopposed by the limits that later generations of stars would face. They blazed into existence in brilliant blue-white glory, bringing light to the cosmos and ending the cosmic dark ages. Those earliest massive stars lived short, spectacular lives. They poured out searing ultraviolet light, which began to transform the surrounding gas. The intense radiation from these stars began to clear the cosmic fog. Around each early star, a bubble of ionized gas expanded like a hot clearing in the cold mist. As more stars lit up, their bubbles overlapped and grew, and gradually the hydrogen fog throughout space was rayonized, transformed from a cool, invisible haze into a tenuous, glowing plasma. Within a few 100 million years, the combined glow of those newborn stars had chased away the cosmic night, turning the once dark universe into a luminous tapestry of ionized gas. Yet as quickly as they appeared, these pioneer stars burned through their fuel and met their violent ends. When they met their violent ends in colossal supernova explosions, they seeded the cosmos with the very first heavy elements. Some of these early titans were so massive that their cores may have collapsed straight into black holes, seeding the first massive black hearts of galaxies. Others perished in rare kinds of explosions that were so complete they left no remnant at all, just brilliant clouds of enriched gas hurtling outward. In doing all this, these pioneers made possible a future they would never see. The first galaxies were in part sculpted by these stars, their gravity and explosions gathering matter and giving structure to what had been diffuse. With each explosion, the ashes of those first stars spread out, mixing into the primordial gas. When new stars formed from that enriched material, they were slightly different, containing traces of those heavier elements. Over many generations, massive stars continued this cycle of enrichment. They created more and more complex elements and distributed them through space when they died. The galaxy became a richer chemical tapestry with every passing eon. Stars could now form with planets around them because the building blocks of rocky worlds, silicon, iron, oxygen, were available where once there had been none. Massive stars have always been the great alchemists of the universe, turning the simplest matter into a menagerie of elements. Through their lives and deaths, they gradually transformed a young, simple cosmos into a mature, complex one. Roughly 10 billion years ago, galaxies swarmed with star birth. It was a time of cosmic exuberance, sometimes called the universe's cosmic noon, when stars were being born at rates far higher than today. Massive stellar clusters lit up young galaxies, and brilliant blue-white light from hot newborn stars shone across the cosmos in great numbers. Massive stars filled early galaxies with intense radiation, and their supernovae pumped energy and momentum into the surrounding gas. Shockwaves from those explosions swept through interstellar clouds, compressing some regions and triggering new rounds of star formation, even as they blew other gas outward to more distant reaches. In this way, massive stars acted as both creators and destroyers on a galactic scale, sparking the birth of new stars even as they tore others apart. Modern telescopes are even now hunting for telltale signs of those first stars in the light of ancient galaxies, pushing our view ever closer to the cosmic dawn. The history of galaxies is written in the light of massive stars. In distant galaxies, we can still observe the aftermath of tremendous starburst events, times when countless massive stars formed together and then died in a cascade of supernovae. Such events can shape entire galaxies, driving winds of gas that stream out into intergalactic space. Some distant galaxies we observe today, like cosmic fireworks frozen in time, are experiencing such starbursts, blazes of creation where dozens of massive stars can explode in rapid succession. Over time, these processes regulate how galaxies grow. Too many supernovae in a small region can temporarily quench further star formation by heating and dispersing the gas. Yet, as the gas cools and settles once more, new stars eventually emerge. It is a cyclic rhythm, periods of frenzied creation punctuated by the calamitous deaths of the creators. For more than 13 billion years, this cycle has continued, and it will persist for countless eons to come. As the universe aged, the furious pace of star formation gradually slowed. The most massive stars had done their work of enrichment and energy injection, and galaxies settled into a steadier rhythm of star birth. Our own Milky Way carries the memory of this long history. In its oldest stars, scientists find only tiny traces of heavy elements, signatures of a time shortly after the first stars seeded the galaxy. Scientists have found stars near our galaxy's center with perhaps 1,000 times less iron than the Sun, relics from an era before many supernovae had spread metals. In contrast, our Sun contains the enriched material of countless predecessors. In younger stars like our Sun, we find a rich array of elements in their makeup, evidence that countless generations of massive stars lived and died before our Sun ever formed. Indeed, the Sun is a child of a more evolved cosmos, born about 4.6 billion years ago in a galaxy already teeming with the chemical products of ancient stellar lives. Consider an atom of iron deep within your blood. Long ago, it was forged in the core collapse of a massive star. When that star exploded, the iron atom was hurled into space among billions of others. For ages it drifted through the galaxy as part of a cosmic cloud. Eventually that cloud clumped and gave birth to new stars and planets. On one of those newborn worlds, our Earth, that iron atom found its way into the rocks, the soil, the water, and finally into you. In this way, a supernova that erupted before our Sun was born left a tiny signature that is carried in your body even now. The calcium in our planet's rocks, the iron in our blood, the oxygen we breathe, none of these existed at the dawn of time. They were manufactured in the cores of massive stars and then scattered across space by stellar deaths. Only after that enrichment could planets like Earth form, bearing solid ground and life's essential ingredients. Every atom of heavy element around us has a lineage that traces back to a star, many of them to the massive stars that erupted in glorious death. Through cosmic time, massive stars have thus been agents of change and progress. They lit the first candles in a dark universe, built up the elemental diversity needed for complex structures, and drove the evolution of galaxies. What began as a nearly pure fog of hydrogen eventually became a universe dotted with planets, oceans, and living creatures, all by virtue of this stellar alchemy. The fires of massive stars forged the tools needed for complexity and life, turning a simple beginning into an ever more intricate cosmos. Even now, in galaxies near and far, the life cycle of massive stars continues to influence the cosmos. In the bright nebulae of nearby galaxies, we see echoes of the first star's role. New massive stars, though fewer than before, are still forging elements and sculpting their environments. And in the far reaches of the universe, telescopes catch the faint glow of ancient supernova, allowing us to peer back in time and witness the moments when the seeds of later galaxies and planets were sown. Time and again, the universe has renewed itself through the lives of stars. Massive stars, with their brilliant but brief existences, are like the strokes of an artist's brush on the cosmic canvas, each supernova adding new color and depth to the picture. Over billions of years, those strokes accumulated into the vibrant tapestry of galaxies, stars, planets, and life that we see today. For now, and for many billions of years to come, the cycle continues unabated, filling the cosmos with light and possibility. For as long as humans have gazed at the night sky, we have felt a profound connection to the stars. In ancient times, people looked up and saw eternal, unchanging lights, pinpricks in the dark dome of night that guided migrations, inspired myths, and marked the passage of time. The stars were thought to be distant and perfect, wholly separate from the realm of Earth. Yet the true relationship between humanity and the stars is far more intimate and surprising than our ancestors ever imagined. Over the centuries, observations gradually revealed that the stars are not eternal or unchanging. In 1572, the astronomer Tycho Brahe witnessed a brilliant new star lighting up the sky. What we now know was a supernova, the explosive death of a distant sun. Its appearance astonished the learned men of Europe and challenged the old belief that the heavens were fixed and unalterable. Centuries earlier, in 1054, astronomers in China and elsewhere recorded a guest star that shone brightly even in daylight for weeks. We now recognize that as the supernova which created the Crab Nebula, a beautiful cloud of glowing debris still visible in telescopes. These events were early clues that stars live and die, and that the cosmos is a dynamic, living tapestry rather than a static backdrop. As science advanced, we learned not only about the life cycles of stars, but also about our own ties to those cycles. Stars, especially massive ones, forge the elements that make up our world and our bodies. The connection is literal. The calcium in our bones, the iron in our blood, the carbon in our cells were all formed in the nuclear furnaces of stars, or in the titanic explosions that mark their demise. Long before the Earth existed, massive stars lived and died, scattering these elements across space. That scattered stardust became part of the cloud that condensed into our sun, our planet, and ultimately every living being on it. It can be a jarring realization. Every atom of oxygen we breathe, and every atom of carbon in our DNA, was once inside a star. In the adage, ashes to ashes, dust to dust, we find a cosmic echo. Everything returns to stardust in the end. We are, in the most real sense, made of stardust. This idea, popularized by scientists and poets alike, speaks to a deep truth about our origin. The very existence of life on Earth is linked to a chain of stellar births and deaths stretching back billions of years. Without the supernova explosions of ancient stars to seed the galaxy with heavy elements, there would be no ground to stand on, no air to breathe, no complex chemistry to spark life's fire. Modern astronomy has given us dramatic illustrations of this connection. When we peer at the glowing remnant of an exploded star through our telescopes, we can identify signatures of the same elements found in our own bodies. In the colourful filaments of supernova debris, scientists detect calcium, sulfur, iron, and more. In fact, one X-ray observation of the Crab Nebula, the aftermath of that guest star of 1054, revealed large quantities of calcium and iron strewn into space. It's humbling to realize that those are some of the very elements now composing our bones and blood. The universe has literally shared its substance with us. Our connection to the stars is not only physical, but also intellectual and emotional. From the myths of ancient civilizations to the musings of modern philosophers, stars have always figured prominently in our attempt to understand existence. We have long told stories about heroes and gods becoming stars, not realizing how fitting it is, since we, in reality, came from them. Knowing that we are made of star stuff adds a sense of kinship with the cosmos. Some people find deep comfort or spirituality in this knowledge, feeling that it connects us to the universe in a profound way. We are no longer mere spectators of the stars. We are participants in their story. The atoms in our bodies have experienced the nuclear fury of a star's core and the transcendent blast of a supernova long before coalescing into us. Through the lens of this knowledge, when we look at the night sky, it becomes a kind of homecoming. We see not just distant, foreign lights, but places our ingredients have been, and destinies our world is tied to. This realization has infused human culture and thought. Some of the earliest stories imagine that we came from the stars, or will return to them. And in a sense, those stories were true. It tells us that the story of the stars is, in some ways, our own story. It also underscores the unity of all life on Earth. Every person, animal, and plant is made of the same cosmic matter. We share a common origin among the stars, a fact which can inspire a sense of oneness with each other and with the universe. We carry pieces of the universe within us, forged in stellar furnaces, scattered across space, and gathered here on Earth. It is a poetic truth, grounded in scientific fact, one that bridges the cold depths of space and the warm sphere of human experience. Standing under a sky full of stars now, we might feel a profound kinship with those twinkling lights. They are our ancient ancestors in a way, the givers of the gifts that made life possible. And as we continue to study them, watching distant supernovae flare, analyzing stardust in our laboratories, tracing the cosmic origins of atoms, we deepen our connection. We have even reached out physically. NASA's aptly named Stardust mission brought back tiny grains of comet dust, material once forged in ancient stars, allowing us to literally touch a piece of stellar history. In doing so, we extend our senses and our presence into the cosmos, further uniting our story with that of the stars. We have become conscious matter, reflecting on the processes that made us. In the end, the relationship between humanity and stars is a circle of understanding and existence. Born from the deaths of stars, we have arisen to contemplate the stars. We use the elements once forged in stellar hearts to build telescopes and detectors to study those very stars. We have become a way for the cosmos to know itself. The next time you glance up at the stars, you might feel compelled to whisper a quiet thank you, for those distant suns have given us everything, including the very breath in our lungs and the spark of thought in our minds. As we contemplate massive stars and their life cycles, we are really contemplating our own cosmic genealogy, and that knowledge, quietly considered under the canopy of stars, can be as comforting and awe-inspiring as the gentle light that falls from the Milky Way on a clear, dark night. From the dawn of time to this very moment, the saga of the stars has been one of ceaseless creation and destruction. Massive stars, with their fierce light and fiery ends, have acted as narrators of the universe's journey. Each generation of stars carries in its bones the ashes of those that came before, and in dying, it prepares the ground for those yet to come. In this way, the cosmos renews itself continuously. It is an endless inferno in which old elements are constantly reborn into new stars, new planets, and new possibilities. If we listen closely to the story that stars tell, we hear themes of transformation and unity. A star forms out of the debris of an earlier star's death, a poignant union of destruction and creation. As it shines, it gives energy and light, perhaps nurturing planets and life around it, shaping new chapters in the cosmic tale. When it dies, it spreads its enriched substance outward, sowing the seeds of future suns. Nothing is wasted. Even the violence of a supernova serves a purpose in the grand design, propagating the building blocks for new worlds. The death of one star might trigger the birth of others, as shockwaves jostle gas clouds into collapsing. The cosmos is always moving forward, weaving old endings into new beginnings. In the great expanse of the universe, countless such stories are unfolding right now. We have witnessed supernovae in galaxies billions of light years away, proving that even in far corners of the cosmos, this stellar life cycle plays out just as it does here in our own galaxy. Elsewhere, in murky nebulae, new stars are kindling into existence, where just before there was only cold dust. The scale is immense and almost beyond imagination, yet the pattern is simple and elegant. Creation follows destruction. Out of fire and ashes comes new light. This endless conversion of stardust to starlight and back to stardust binds the universe's past, present, and future together. It has been so for billions of years and will continue for billions more. For more than 13 billion years, this cycle has continued, and it will persist for countless eons to come. We, as observers and participants in this universe, find meaning in these eternal cycles. We see in the stars a reflection of processes that resonate with us: birth, life, death, and rebirth. There is a certain comfort in the continuity of it all. Generations of stars have come and gone, stitching together the fabric of our galaxy. Our own sun is a beneficiary of that cosmic lineage, born in the aftermath of countless stellar lives and destined to contribute its matter back to space in the far future. When we recognize this, we see how connected everything is. The gold in a ring on a person's finger may have been forged in a neutron star collision billions of years ago. The calcium in our teeth was brewed in a supernova before the Earth existed. The narrative threads run deep, linking us and everything we know to events unimaginably distant in time and space. Thus, the massive stars we have followed, from their dusty origins to their cataclysmic finales, are more than just isolated points of light. They are the universe's storytellers. If the universe is a grand stage, then the stars are both actors and narrators, each supernova a dramatic climax that propels the narrative forward. Their very existence and demise chronicle the evolving cosmos. They speak of a universe that is dynamic and alive, constantly renewing itself through dramatic events. Through their light, they whisper tales of how galaxies grew and changed, how the elements were made, how the stage for life was set. And even after they are gone, their stories live on in the materials they leave behind, and in the light that continues travelling, perhaps to the eye of a distant observer, or the lens of a telescope far in the future. As we reflect on this portion of our journey, we remain aware that the story is far from over. It is humbling to think we inhabit a universe where such cycles occur, and even more humbling that we have the chance to witness and comprehend them. The night sky above us is a living narrative, with new chapters being written in stellar furnaces as we speak. Each bright supergiant, each faint remnant nebula, is a sentence in that never-ending epic. We humans have only recently learned to read this cosmic story, but already it has filled us with wonder and insight. How many cycles of stellar death and rebirth preceded us, and how many will follow long after we are gone? The numbers are beyond comprehension, yet we know these processes will continue, carrying the cosmic narrative onward. The endless inferno of creation and destruction will continue to blaze across the cosmos, and with it, the story of the universe will continue to unfold. In that eternal cycle, there is a promise that existence is never static, that from every end, a new beginning will arise. In the grand scheme, nothing is truly lost, only changed, as the cosmic furnace keeps turning darkness into light and back again. The stars assure us that even in the vast darkness, light always returns. And as long as there are eyes to see and minds to wonder, the story of the stars will never truly end.